Have you ever looked up at the night sky and wondered, where did it all come from? Why does the universe exist? And why are we seemingly the only existing life? Join us as we explore one of humanity's most profound questions. How did the universe begin from nothing? Imagine a time when the universe was compressed into an incredibly hot, dense singularity. This state existed approximately 14 billion years ago and is described by what we now call the Big Bang theory. According to this theory, the universe began as a singular point that suddenly expanded and continues to expand today. This expansion didn't involve an explosion in the conventional sense, but rather a swift and immense stretching of space itself. As this initial rapid expansion occurred, particles began to form, eventually coalescing into atoms and simple elements like hydrogen and helium. Over millions of years, these elements gathered under the influence of gravity, forming stars, galaxies, and ultimately the vast cosmos we observe today. Cosmic microwave background radiation, a faint glow left over from the early universe, provides compelling evidence supporting the Big Bang theory. This radiation acts as a sort of cosmic blueprint, filling every inch of the cosmos and offering a snapshot of the universe when it was only about 380,000 years old. Observations made from satellites and telescopes have allowed scientists to measure these ancient microwaves, revealing subtle fluctuations that correspond to the initial conditions of the universe. Such scientific breakthroughs have refined our understanding, providing a glimpse into the epically grand processes that birthed the universe from a seemingly minuscule start. The evidence supporting the Big Bang theory is both compelling and diverse, offering a multifaceted confirmation of one of the most profound events in the history of our universe. One of the most significant pieces of evidence is the cosmic microwave background radiation, discovered accidentally by Arrow-Penis and Robert Wilson in 1965. This faint afterglow is a remnant of the early universe, dating back approximately 380,000 years after the Big Bang Gang. The CMB provides a snapshot of the infant universe, revealing temperature fluctuations that help shape the large-scale structure of everything we see today. These minute variations, measured with extraordinary precision by instruments like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have offered irrefutable evidence of the universe's hot, dense beginning and subsequent expansion. Another robust pillar supporting the Big Bang theory is the observable redshift of galaxies. Initially noted by Edwin Hubble in the late 1920s, this redshift reflects the fact that galaxies are moving away from us in all directions. According to Hubble's law, the farther a galaxy is, the faster it appears to be receding. This cosmic dance of galaxies uniformly moving apart is consistent with the notion that the universe is expanding, a key prediction of the Big Bang theory. Additionally, the abundance of light elements such as hydrogen, helium, and lithium observed throughout the universe aligns well with predictions made by Big Bang nucleosynthesis models. These models suggest that the conditions in the first few minutes after the Big Bang were just right for forming these elements in precise proportions. Collectively, the CMB, redshift of galaxies, and primordial element abundances weave a compelling narrative that underscores the Big Bang theory, knitting together various strands of observational data into a cohesive cosmic story. The question of what conditions existed before the Big Bang plunges us into the murky waters of the unknown, a domain where even the most advanced scientific models grapple for clarity. According to standard cosmology, the Big Bang represents the origin of time and space as we understand them. In this model, asking what came before is somewhat analogous to asking what lies north of the North Pole, essentially suggesting that the very concept of before becomes meaningless. However, speculative theories drawing from quantum mechanics and advanced theoretical physics offer some tantalizing ideas. One such proposal involves the notion of a pre-Big Bang state, dominated by a quantum vacuum, a seething froth of probabilistic events governed by the principles of quantum mechanics. In this view, the universe could have emerged from a vacuum fluctuation, where a temporary disturbance in this quantum state resulted in a Big Bang-like event. Another intriguing hypothesis is the concept of a cyclic universe. where big bangs and big crunches occur in a continuous loop. In this model, our current expansion might eventually reverse, leading to a future collapse that precedes another big bang. Moreover, some theories suggest the presence of a multiverse, where our universe is just one bubble amid a frothy sea of universes, each with its own physical laws and constants. These speculative frameworks push the boundaries of our understanding, offering differing visions of what might have preceded the grand cosmic dawn marked by the Big Bang. In the vast silence of space, something extraordinary has broken through. The universe's secret whisper turned deafening, a flash so bright, so sudden, it seemed to tear through the darkness like a cosmic scream. For decades, astronomers have searched the stars, chasing fleeting signals, mysterious ripples in the fabric of the cosmos. But then, on a routine night, something unprecedented happened. An intense burst of radio waves, faster and brighter than any before, vanished as quickly as it appeared. It defied explanation, challenging everything we thought we knew. Is it a sign of alien life, a portal to another universe, or something even stranger lurking at the edge of reality? Tonight, we unravel the shocking discovery that could rewrite our understanding of space, leaving us questioning if we've truly glimpsed the universe's deepest secrets, or if the universe itself is hiding something terrifying. It all began with a routine survey of a distant galaxy cluster, an area astronomers had studied for decades. Using a state-of-the-art radio telescope array, they were hunting for faint signals that might hint at the universe's unseen structures. On an otherwise typical night, something unusual caught their attention. An intense, quick burst of radio waves that seemed to come from nowhere and fade almost as fast as it appeared. This wasn't the first time astronomers had recorded such fleeting signals. Fast radio bursts, or FRBs, had been sporadically observed over the past decade. They appeared as incredibly short-lived flashes lasting mere milliseconds, yet their intensity suggested an enormous amount of energy packed into a tiny space. The challenge was that their origins remained a baffling mystery. But this particular burst stood out. It was brighter than most, and its signal had peculiar characteristics that defied the usual explanations. The astronomers examined the data meticulously, cross-referencing with observations from other telescopes around the world. What they found was startling. The signal was so intense and so fleeting that it seemed almost impossible to produce by conventional astrophysical phenomena. Initially, they thought it might be interference or a terrestrial source, perhaps a malfunction in the equipment or a signal bounce off a satellite. Such explanations had momentarily explained similar signals before. But this time, efforts to dismiss it as interference failed. The signal was too clean, too precise, and exhibited features characteristic of genuine cosmic origins. Further analysis revealed key anomalies. The signal contained an unusual spectrum with certain frequencies oddly amplified while others were suppressed. It also exhibited a polarization pattern unlike anything seen in typical astrophysical events. These clues hinted at a more exotic origin, perhaps something beyond the known mechanisms of neutron stars or black hole activity. Over the next weeks, the team verified their observations. They used multiple telescopes spanning the electromagnetic spectrum, radio, X-ray, and gamma-ray observations to catch any counterpart signals that might shed light on the burst's source. Yet despite their efforts, no associated emissions were detected. The burst seemed to be a one-off event with no repetition. The initial mystery deepened because the burst's brightness suggested a source in a galaxy billions of light-years away. This implied an energy release that dwarfed any known stellar process. The astronomers wondered, what kind of cosmic object or event could produce such a brief but powerful signal from so distant a place? A particularly perplexing aspect was the burst's high degree of polarization. In simple terms, polarization relates to the electromagnetic wave's orientation. Such a feature often points to a magnetic field involved in the emission process. Yet, the specific pattern they observed didn't match models of known magnetic phenomena around neutron stars or pulsars. Adding to the intrigue, the dispersion measure, the way the radio waves had spread out as they travelled, indicated the signal had travelled through a dense cosmic medium. This suggested a location embedded deep within a galaxy's core, possibly near a supermassive black hole or an active galactic nucleus. However, the most puzzling feature was its brevity combined with its intensity. Known explosive events like supernovae or gamma-ray bursts couldn't produce such rapid, intense flashes without leaving detectable aftereffects. Other models, such as star collisions or magnetic reconnection events, also didn't fit the data. As the team examined the data, extraordinary hypotheses arose. Was this from an advanced extraterrestrial civilization? Could it be a natural but unknown phenomenon? Perhaps a new class of cosmic object or process that defied current understanding? The data hinted at something fundamentally different from anything previously documented. The initial observations sparked a whirlwind of theories, debates, and further questions. Many scientists remained skeptical, insisting that extraordinary claims required extraordinary evidence. Still, the data persisted, suggesting a genuinely novel phenomenon, something that could rewrite parts of astrophysics. Over subsequent months, astronomers recorded more bursts with similar features, but each arrived unpredictably, like messages from an unknown cosmic sender. Some bursts appeared isolated, others followed patterns, though none were decipherable. The lack of repetition and random timing only deepened the mystery. What was clear was that this object or phenomenon was unlike anything catalogued before. Its sheer energy, combined with its fleeting nature, placed it at the edge of scientific understanding. It prompted speculation about a new kind of cosmic engine, perhaps a new stellar remnant, a highly magnetized object, or even something more exotic. A cosmic riddle challenging current astrophysics. As more data were collected, the scientific community became captivated. The discovery led to questions about whether this indicated a hidden population of objects. Was there a new mechanism producing bursts that current theories couldn't explain? Could the universe be speaking to us through these signals? The initial observation, seemingly innocuous, a quick, intense burst of radio waves from distant space, had actually opened a Pandora's box of cosmic mysteries. Whatever caused it was extraordinary, and unlocking its secrets might reveal insights into the universe's most elusive energetic phenomena. The mounting evidence suggested humanity stood on the threshold of a revolution, one that could fundamentally alter our understanding of the cosmos and our place within it. Word count 855. The data collected from these mysterious objects sent ripples of disbelief through the astrophysics community. For decades, scientists relied on well-established models to interpret the cosmos, guided by physics and observable celestial phenomena. But what was uncovered refused to fit within those frameworks. It was as if the universe had handed over a puzzle piece shaped entirely differently from everything else in the set. At the core was something defying fundamental laws of physics as we understood them. Imagine observing a signal emanating from a distant galaxy. A signal that was remarkably powerful and exhibited a pattern of behavior that directly contradicted known principles. For instance, the intensity and frequency shifts observed far exceeded predictions for sources at such distances. Traditionally, objects like quasars, pulsars, or black hole accretion disks emit radiation with predictable signatures, energies, emissions, and variations all aligning with models developed over the past century. Yet, these signals shattered that consistency. One glaring way the data defied expectations involved the frequency drift of the signals. Normally, signals from cosmic sources are influenced by the universe's expansion and local motion, leading to predictable redshift or blue shift. But these signals showed frequency variations that couldn't be explained by cosmic expansion or known celestial motions. Instead, they exhibited rapid, erratic frequency changes that bore no relation to any known astrophysical process. These shifts were too dramatic, sudden, and inconsistent with gravitational or electromagnetic effects from any known source. Adding to the mystery was the intensity of the signals. Some emitted energy blatantly violated the inverse square law, which states brightness diminishes with the square of distance. Instead, astronomers observed signals seeming to emanate from sources incompatible with their models of energy emission. For example, the emissions appeared to intensify in bursts that vastly exceeded the outputs of supernovae, gamma-ray bursts, or active galactic nuclei. These bursts were more energetic than expected, with no identifiable precursor or pattern, as if something entirely new was at play. The polarization patterns further deepened the enigma. Natural electromagnetic emissions from celestial objects tend to exhibit certain polarization characteristics informative about magnetic fields, plasma, or scattering processes. The signals, however, displayed polarization states inconsistent with any known emission mechanism. They varied rapidly and unpredictably, implying either an environment unlike anything known, or that we were observing a phenomenon outside current astrophysical paradigms. Spectral analysis compounded the mystery. Instead of the smooth spectra expected from natural objects, these signals showed irregular spikes and dips across a broad range of frequencies. They bore signs of interference, yet no terrestrial or solar system origin could account for them. It was as if the signals arose from an environment with properties unlike any known cosmic setting, possibly dominated by unknown particles or field interactions that defy current understanding. Even the timing of the signals posed questions. Natural phenomena like pulsars pulse with extraordinary regularity, and gamma-ray bursts follow predictable temporal profiles. But these signals arrived in irregular, unpredictable bursts, some lasting mere milliseconds, while others persisted for seconds or minutes. What disturbed researchers was their apparent lack of connection to cosmic clocks or cycles. They seemed random yet purposeful, perhaps indicating a new kind of source or process altogether. The pattern, or lack thereof, in the arrival times added to the puzzle. A standard model would predict randomness within a statistical framework. Instead, the signals showed a coherence hinting at intelligence. Some argued their timing bore the hallmarks of deliberate modulation, patterns suggestive of encoding, messages, or signalling beyond natural phenomena. Skeptics questioned these interpretations, but the data could not be dismissed as cosmic noise. The cumulative impact on theories of cosmic distances and energy scales was profound. If these signals originated from sources billions of light-years away, their incredible energy outputs implied sources capable of unleashing energies rivaling entire galaxies. This directly contradicted the idea that only extreme objects like quasars or active galactic nuclei could produce such intense emissions. Some researchers even proposed the possibility that these signals indicated an unknown energy or matter form, perhaps related to decay or interactions of hypothetical particles from the universe's early moments. Furthermore, the observed spectrum did not match any known emission process. Natural astrophysical emissions tend to fall into predictable categories: thermal radiation, synchrotron radiation, inverse Compton scattering, each with characteristic spectra. But these signals did not conform to those patterns. Instead, they involved irregular non-thermal spectral components defying classification. Such unclassifiable spectra suggested mechanisms operating through physics beyond current theories. The most troubling aspect was the consistency of certain features across observations. Whether signals came from different sky regions or times, they shared peculiarities: erratic polarization, rapid shifts, intense bursts. This suggested a common underlying cause, distinct from natural objects. It hinted at a new class of cosmic phenomena that could unveil new physics or offer insights into the universe's nature. Ultimately, these anomalies challenged and shattered current models. They revealed something fundamentally incompatible with the physics frameworks previously held. There was a dissonance impossible to ignore, a call for radical rethinking of cosmic possibilities. It was as if the universe was whispering secrets in a language we didn't yet understand, perhaps requiring new theories, tools, and paradigms to decipher. Detecting this extraordinary phenomenon required highly sophisticated instruments, cutting-edge technology, and international collaboration. An orchestra of scientific ingenuity working tirelessly to peel back cosmic mysteries. The first instrumental hero is the Very Large Array, VLA, in New Mexico. This array of 27 radio antennas, each the size of a football field, functions as a single enormous telescope. When tuned correctly, the VLA detects faint radio waves from the universe's farthest reaches with astonishing sensitivity. Its ability to synthesize a larger aperture via interferometry enables precise localization of cosmic signals, scanning vast sky areas and recording transient radio emissions that last mere milliseconds. But the VLA's role was just the beginning. Detecting this strange space signal also depended heavily on the Canadian hydrogen intensity mapping experiment CHIME in British Columbia. CHIME is a groundbreaking instrument composed of 4 large cylindrical radio telescopes. Its design allows it to survey a significant part of the sky simultaneously, monitoring for rapid brightening of signals, known as fast radio bursts. When the signals first appeared, CHIME was the first to notice their peculiar nature. Its real-time data processing enabled immediate alerts, helping the global community mobilize to study these fleeting phenomena. Complementing ground-based telescopes was the role of space detectors, specifically the Fermi Gamma Ray Space Telescope launched by NASA. Fermi observes gamma rays, the most energetic electromagnetic radiation, crucial for multi-wavelength astronomy. When radio telescopes detected anomalous signals, Fermi checked for concurrent high-energy emissions. Its observations helped determine if the phenomenon was associated with energetic events like gamma-ray bursts, magnetar flares, or something unknown. Similarly, the European Space Agency's Integral satellite observed gamma rays and X-rays, providing additional data points to confirm whether counterparts existed in high-energy spectra. Coordination among ground and space telescopes, sharing data in real time, created a multi-layered observational network, drastically improving the chance of catching signals across different wavelengths. Optical telescopes like Keck in Hawaii and the Very Large Telescope, VLT in Chile, added crucial pieces. They searched for any visible counterparts, brightening or anomalies, around the source. Although no direct optical emission has been definitively linked so far, these observations are vital in ruling out certain astrophysical objects and processes. All these instruments are integrated into a global alert system, an evolving network that instantly shares data when a transient signal is detected. The system employs real-time data processing algorithms designed to sift through massive incoming information. These algorithms, incorporating machine learning, quickly flag signals of interest, ensuring rapid follow-up observations. This mobilization helps maximize understanding of the event. Advances in digital signal processing technology have been integral. High-speed analog-to-digital converters transform radio signals into digital data streams for complex real-time analysis. These technological improvements ensure fleeting signals, lasting milliseconds, are captured without loss of information, stored, and analysed with increasing precision. The enormous data generated is processed by supercomputers and cloud systems, applying sophisticated algorithms to distinguish signals from cosmic noise. Pulsar timing arrays played an indirect but significant role. Pulsars, neutron stars emitting regular beams of radio waves, serve as cosmic metronomes. Variations in their timing can reveal influences from gravitational waves or space-time disturbances, helping create broader context and test theories related to unseen cosmic influences on space signals. Another technological advance is the development of ultra-wideband receivers. Capable of capturing a broad spectrum of frequencies simultaneously, these receivers are crucial if the unknown signals emit across a wide range. They enable detailed spectral analysis, shedding light on the origin and mechanisms of the phenomenon. Data storage and sharing are also vital. Distributed computing networks and international collaborations like the Square Kilometre Array, SKA, facilitate global data sharing, allowing astronomers from Australia to Europe, North America to Asia to work seamlessly. High-capacity storage ensures no signals are lost to overflow, preserving information for post-processing. Autonomous real-time detection systems monitor data streams continuously, flag anomalies, and trigger follow-ups automatically, reducing response times. This transformation from waiting to immediate pursuit accelerates understanding. Spectrometers attached to large telescopes analyze the signal's energy spectra, revealing environmental details. Dissecting spectral components helps identify whether signals originate from known phenomena like pulsars, quasars, or magnetars, or if they are entirely new. The success of detection hinges on the synergy between these instruments, technological innovations, and collaborative effort. This global network of observatories, detectors, and tools exemplifies humanity's relentless drive to understand cosmic enigmas. Without this technology, supercomputers processing data rapidly, ultra-sensitive radio detectors, space telescopes probing high-energy regimes, the signals would remain hidden amid cosmic noise. As analysis continues, it's clear this marks a turning point in observational astronomy. Each data piece, captured from a worldwide network, brings us closer to understanding whether this is a new class of cosmic object, an indicator of unknown phenomena, or something fundamental about reality itself. The technological achievement involved underscores scientific progress and hints at many more discoveries lurking in the universe's dark corners. Before the recent discovery that has everyone buzzing, subtle signals and anomalies in space data seemed insignificant, or just the universe's quirks. These hints now appear like faint cracks in a celestial puzzle, clues that, in retrospect, pointed towards something extraordinary lurking beyond our understanding. One of the earliest whispers came from radio astronomy. Decades ago, scientists detected unusual radio pulses from a particular sky region. These pulses didn't follow patterns of known phenomena like pulsars or quasars. Instead, they displayed strange irregularity, burstiness that defied models. It wasn't just quick flashes of energy. What puzzled astronomers was the consistency with which they appeared, almost like a deliberately encoded signature. At the time, many shrugged it off as instrumental noise or atmospheric interference. The universe's background static made distinguishing genuine signals from noise notoriously tricky. Then came the enigma of fast radio bursts, short, intense radio flashes that appeared suddenly and vanished. First observed in the early 21st century, their origins were debated. Some believed highly energetic processes like collapsing neutron stars or black holes caused them. Others speculated they might be alien signals. Amid this chaos, researchers noticed peculiar patterns, repetition in some bursts, unusual dispersion measures, and polarization features hinting at complex structures beyond natural events. These details didn't fit neatly into existing models but prompted ongoing investigation. As more data accumulated, scientists observed a disturbing trend. Certain space regions radiated excess electromagnetic energy at specific frequencies. These subtle but persistent anomalies didn't align with known objects. Some claimed they could be echoes from cosmic events or remnants of early turbulence. Others argued they might be instrumental artifacts. The recurring signals suggested more than mere calibration errors. A significant aha moment emerged during targeted deep space surveys showing discrepancies. Data from multiple telescopes confirmed persistent anomalies. Patterns showed signals concentrating in particular areas, forming a kind of gravitational or electromagnetic nexus, defying current astrophysics explanations. Could they be distortions from massive unseen objects, interaction zones where space behaves strangely? Or, more tantalizing, they might indicate deliberate signals from an intelligence or extraterrestrial technology beyond our wildest hypotheses. Anomalies extended beyond electromagnetic observations. Gravitational wave detectors, designed to catch ripples from black hole or neutron star mergers, occasionally registered unexplained, faint signals. Instead of expected signatures, detectors picked up peculiar low-frequency disturbances with no known origin. Skeptics initially attributed these to artifacts or terrestrial noise. Further research revealed more irregularities. Infrared, ultraviolet, and X-ray surveys detected faint anomalous emissions clustered irregularly in space and time. These emissions hadn't matched any known celestial bodies, no stars or galaxies, only diffuse signals with unique spectral features. It was as if an invisible, intelligent agent dispersed signatures across wavelengths, leaving faint breadcrumbs. As technology advanced, scientists re-examined archival data, uncovering interconnected clues. Anomalies persisted across different observations and instruments, often near regions where large mysterious structures appeared later or synchronously with gravitational anomalies impossible to explain with known physics. This pattern suggested a possible link between these signals and unseen phenomena. Another crucial piece of evidence was the detection of unusual variations in the cosmic microwave background, CMB. Tiny fluctuations, once deemed insignificant, sometimes aligned with other anomalies' locations. It was as if the universe wove threads of signals and disturbances into a bigger cosmic tapestry, hinting at systems or objects with properties outside natural astrophysics. Despite these clues, the scientific community remained cautious. Many argued that the anomalies were natural eccentricities, quantum effects, unknown particles, or unrecognized astrophysical processes. Others demanded more data, better observations, and refined models. Yet the pattern was hard to ignore. Space had kept its secrets behind layers of noise and chaos. Still, in that noise, a whisper persisted, suggesting the universe wasn't as empty or random as it seemed. Recent years brought a convergence of data and advanced tools that sharpened focus on the anomalies. Patterns appeared more deliberate, more structured, no longer mere cosmic coincidence. It became impossible to dismiss the possibility that these signals and peculiar patterns represented something fundamentally different, signs of being watched or communicated in ways beyond current understanding. All these prior hints, once dismissed or overlooked, are now seen as the trailheads of humanity's most profound discovery. that we are not alone, or at least part of a universe teeming with entities or phenomena that challenge our understanding. The question isn't just whether we're listening, it's whether we're prepared to understand what whispers in the vast dark space surrounding us. In short, what once seemed like random noise or background static now points toward a tapestry of signals, clues threading together a picture of the universe far more complex, intelligent, and interconnected than previously believed. These anomalies are more than mere curiosities. They are the faint outlines of a cosmic conversation, waiting for us to listen, interpret, and perhaps finally understand. As technology improves and our curiosity deepens, the universe's secrets are slowly revealing themselves, promising answers, or more profound questions about our place among the stars. The true nature of this mysterious object remains elusive, with its physical properties, mass, size, and composition shrouded in uncertainty. Scientists analyze available data, revealing fragments of an ancient cosmic puzzle that defy conventional understanding. Consider first the apparent size of the emitting region. The rapid rise and fall times of the radio burst, just milliseconds, suggest an incredibly compact source. Since light travels about 300,000 km/sec, a pulse lasting a few milliseconds indicates an object no larger than a few hundred kilometers across, comparable to a small city or large mountain range. This brevity constrains the emitting region to an extremely tight, dense space, with potentially extreme physical conditions. Determining mass is more challenging. The signals originate billions of light-years away and do not directly convey mass information. However, by examining dispersion measures, the way the signal spreads across different frequencies, researchers estimate the plasma the signals have traversed, offering indirect clues. The host galaxy is highly active, with a supermassive black hole at its core, and surrounding environments are energetic. This suggests the progenitor might be a dense astrophysical object, possibly a neutron star, a black hole, or an exotic compact entity, with several times the Sun's mass confined within a tiny volume. On composition, the question becomes more tantalizing. Spectral data reveal unusual polarization and energy signatures, implying the object isn't composed of ordinary matter. The signals indicate strongly ordered magnetic fields and energetic processes. Such intense polarized emissions typically come from neutron stars or magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These dense iron core objects could, under certain conditions, generate energetic bursts rippling through space. However, the composition appears inconsistent with typical objects. Spectral anomalies suggest an environment rich in plasma and magnetic energy, possibly involving exotic states of matter or unknown particles. Some scientists propose the object might be a form of condensed matter under extreme magnetic confinement, an unusual phase of matter existing only in such powerful fields. Others speculate about deformed or quark matter cores, a hypothetical state where protons and neutrons break into quarks, forming a dense exotic core within a neutron star or a more mysterious dense body. Adding complexity, the signals show high polarization levels, pointing to a highly ordered magnetic environment. This aligns with strong magnetic fields embedded within the object, an uncommon trait for dense astrophysical bodies, yet characteristic of magnetars. These objects, formed from collapsing massive stars, could generate the conditions necessary for such energetic polarized emissions. Yet, the specific polarization directions and spectral features hint at unknown magnetic phenomena or even artificial field generation, raising questions about the true nature of the object. In terms of mass, considering the energy released and inferred density, the object likely belongs to ultra-compact bodies like neutron stars or more exotic remnants. Estimated masses, inferred from gravitational influence and energetic behavior, fall between 1 and 2 solar masses, compressed into spheres just a few kilometers across. Such densities are astronomically high. A teaspoon of matter from this object could weigh billions of tons. This extreme density raises further mysteries, as such objects are at the limit of physical possibility as we understand it. Beyond known celestial bodies, possibilities include dark matter nuggets or primordial relics from the early universe, cloaked in dense plasma and capable of electromagnetic interactions we haven't yet grasped. Or perhaps the object is made of even more exotic matter, byproducts of higher dimensional physics, or manifestations of a new fundamental force. The composition also influences hypotheses about its origin. Could it be a natural formation resulting from stellar remnants or cosmic collisions? Or could it be something more provocative, an artifact of intelligent design? While such ideas remain outside mainstream science, the anomaly of the signal leaves open the possibility of non-natural origins, fueling debates about the universe's true nature. A key challenge is that these signals do not match any known astrophysical phenomena. Pulsars, black hole accretion disks, gamma-ray bursts, or supernova remnants do not fully explain what's observed. Instead, the data suggest a potential new class of cosmic object, one that blurs the line between known physics and the unknown. The implications are profound. If natural, this discovery could expand our understanding of matter under extreme conditions, magnetic dynamics, or plasma physics, perhaps even revealing new states of matter. Alternatively, if signs of artificiality or technological origin are present, then the very framework of life, consciousness, and civilization would need re-evaluation. Such a find might suggest that intelligent entities are involved, manipulating or harnessing such phenomena. Much remains unexplained. The physical properties, mass, size, and composition are still inferred, estimated, and debated. The true nature may involve a combination of mass density, exotic matter, and magnetic energy, or phenomena beyond current theories, awaiting further investigation. The discovery pushes the boundaries of scientific possibility, challenging existing models and inspiring new questions about the universe's most extreme objects. It reminds us that much of the cosmos remains hidden, waiting to challenge our notions of reality, spark curiosity, and fuel the eternal quest to understand. This enigmatic signal hints at phenomena beyond our comprehension, possibly revealing new physics or cosmic entities. Its high polarization, spectral anomalies, and energetic signatures suggest an environment rich in magnetic and plasma phenomena, possibly involving exotic matter. Such properties could be consistent with known objects like magnetars, but may also point toward unknown or artificial origins. If it's a natural object, it could represent previously unseen states of matter under intense magnetic fields or extreme densities. Its inferred density, billions of tons per teaspoon, pushes existing physics toward its limits. If instead signs of intelligence or technology are involved, it might signal advanced civilizations or alien constructs, raising profound questions. The mystery underscores how much we have yet to learn about the universe's complexities. Each clue challenges our theories, broadening our perspective of what's physically possible. Whether a natural phenomenon or an artifact of intelligence, this discovery encourages us to think beyond current boundaries, about the fundamental nature of matter, energy, and possibility itself. In the end, our understanding remains incomplete. The physical properties are reconstructed from indirect evidence, with many facets still speculative. As new data emerge, we may uncover the true nature of this object, possibly revealing novel physics or alien technology, and perhaps opening a new chapter in our cosmic understanding. The luminosity and spectral data of this mysterious signal challenge classification when compared to known celestial objects. It flickers intensely, emitting a burst of energy that, if observed within our galaxy, would rival the brightness of the most luminous objects in the universe. Its fleeting nature, lasting mere milliseconds, compounds the mystery, as during this brief moment it releases an enormous amount of energy, comparable to what our sun emits over several days. Concentrating such energy into such a short window is extraordinary. Luminosity measurements depend on apparent brightness and distance. The signal originates from a galaxy millions of light years away, making its apparent brightness seem modest. However, after accounting for distance, its intrinsic luminosity ranks among the most energetic phenomena recorded. For comparison, the brightest radio bursts in the Milky Way, giant pulses, are several orders of magnitude dimmer, indicating an extremely powerful source. Spectral data further complicates the picture. Its spectrum, the distribution of intensity across frequencies, reveals features totally alien compared to known sources. Most natural radio sources like pulsars, supernova remnants, or active galactic nuclei display spectra fitting certain patterns. Pulsars, for example, usually exhibit a spectrum declining smoothly at higher frequencies following a power law. Supernova remnants and active galactic nuclei have characteristic emission lines or broad components indicating diverse physical processes. Yet, this signal's spectrum defies these categories. It shows an unusual polarization pattern, strongly polarized in a way rarely observed, suggesting a highly ordered magnetic field at its origin. Its spectral energy distribution appears narrow, centered at a specific frequency with a bandwidth considerably narrower than typical astrophysical emissions. This narrowness hints at a very localized, coherent emission process rather than a broad, incoherent one. Even more peculiar are the energy spectrum's features. Instead of following the typical decline with increasing frequency, it exhibits several bright peaks, spectral spikes, across a narrow band resembling lightning strikes. These spikes sometimes shift slightly over time, indicating dynamic conditions at the source. Such fine structure is rare in natural celestial objects, especially over a broad frequency range and with the timing and brevity observed. Pulsars, rapidly rotating neutron stars, produce bursts with high luminosity and sometimes show narrow spectral features, but their signals tend to be regular and predictable, rotating with measurable periods. Supernova remnants are stable, broadband emitters, not fleeting, sharply peaked bursts. Active galactic nuclei can produce intense radio jets, but these are typically sustained emissions over long periods, not transient flashes. The contrast is sharper with magnetars, neutron stars with intense magnetic fields, capable of emitting enormous bursts. Some are bright with complex spectra, but these last longer, seconds to minutes, and feature smoother spectra with broad emission lines. The signal here appears as an abrupt, isolated spike, with a spectrum showing discrete spikes rather than a broad profile. This disparity extends into the energy domain. Known radio-emitting celestial objects generally have luminosities predictable by established physics. The energy released from this signal, once corrected for cosmic distance, exceeds expectations for natural phenomena of similar scale. This suggests an unprecedented natural event or something entirely different, possibly an artifact of a hitherto undiscovered physical process. Its spectral polarization deepens the enigma. Many natural radio sources have some polarization, often linked to magnetic fields, but this signal's remarkably high polarization, nearing 50% in some segments, hints at a highly ordered magnetic environment at the source. Such a high polarization level is uncommon in transient high-energy events, implying a universe-scale magnetic structure might shape or channel its emission. These spectral and luminosity anomalies raise profound questions about the mechanisms behind the burst. Traditional models, shock acceleration or plasma instabilities, haven't reproduced the narrow spectral spikes and high polarization simultaneously. These features align more with coherent emission processes, akin to laser physics but on cosmic scales, yet such processes are rarely observed in natural astrophysical events with such energy outputs. Furthermore, observations across wavelengths, radio, optical, X-ray, show no signals to pinpoint the source. Typically, highly energetic events like supernovae or neutron star mergers leave multi-wavelength signatures. In this case, spectral data indicates a pure radio phenomenon, adding another layer of enigma. The mismatch with known objects is glaring. It doesn't resemble a typical pulsar's emission profile, nor does it match broadband, multi-wavelength emissions from supermassive black holes or supernova remnants. Its luminosity far exceeds most natural transient events, and its spectral structure suggests a quasi-coherent process, perhaps even artificial, though caution remains prudent. Some researchers speculate this could be a new class of celestial object or process, possibly a cosmic hummingbird flitting through the universe's emptiness with bursts of energetic polarized radio emission. Alternatively, it might signal an entirely different phenomenon, such as a natural plasma process yet to be understood, that produces highly localized coherent emissions at specific frequencies with enormous energies. Or more provocatively, could it be evidence of artificial origin? The spectral spikes and high polarization, combined with immense energy output, resemble signals from an advanced civilization using highly directed, coherent communication methods. While highly speculative, such questions challenge our understanding of physics and the potential existence of extraterrestrial intelligence. This rare, bright burst's luminosity and spectral profile do more than set it apart. They threaten to reshape current astrophysical paradigms. Every aspect, from its intense energy over a blink to its narrow spectral spikes and polarization, makes it a tantalizing puzzle. It pushes physics to its boundaries, hinting that processes, natural or possibly artificial, operate under rules we have yet to grasp. As astronomers analyse these spectral signatures, the questions multiply, urging us to re-examine cosmic assumptions and approach with renewed caution. The data suggests this could be a new class of astrophysical phenomenon, or something entirely different. Its features challenge existing models, and its origins remain uncertain. The possibility of artificial origins, though speculative, cannot be outright dismissed, especially considering the high polarization and spectral spikes. Whether natural or artificial, this signal highlights fundamental gaps in our understanding of energetic processes in the universe. Every detail, from its concentrated energy to its spectral features, demands rethinking high-energy astrophysics. It might be a one-of-a-kind natural event, or something more extraordinary. Its signatures point to mechanisms beyond current theories, possibly involving highly coherent emission processes, extreme magnetic environments, or even artificial origins. As more data is gathered, deciphering this enigma could unlock new physics, new understanding, and perhaps alter our cosmic perspective. This might be a new class of astrophysical phenomenon or something entirely different. Its unique features challenge existing models, and its origins remain uncertain. The potential artificial signatures, remarkable polarization and spectral spikes are compelling. Whether natural or artificial, this signal questions the understanding of energetic processes, pushing beyond known physics and inviting us to explore the possibilities. In sum, every aspect of this burst, from its incredible concentrated energy to its spectral peculiarities, demands a reassessment of high-energy astrophysics. It could be a singular natural event or something more extraordinary. Its signatures point to processes operating under rules we have yet to fully comprehend, possibly involving coherent emission, extreme magnetic fields, or even artificial intelligence. As more data is analysed, unlocking its secrets could revolutionize our understanding of the universe, revealing phenomena beyond current models and possibly hinting at intelligent activity or undiscovered natural physics. The signals are unlike anything astronomers have encountered. They appear as brief, intense flickers of radio energy, lasting mere milliseconds but leaving a mark on detectors. These flashes are rare and unpredictable, emerging from space without warning and vanishing quickly. Their spectral profile adds to the mystery. They don't conform to common cosmic patterns, spreading across a broader frequency range than typical natural signals. Some frequencies show exaggerated intensities, others remain subdued. Most striking is their polarization. Polarization refers to the electric field's orientation. Natural processes tend to follow predictable behaviors dictated by magnetic fields or environments. Here, polarization is highly variable, fluctuating rapidly and defying explanation. Sometimes the waves are linearly polarized along one plane. At other moments, they shift to circular polarization or become elliptical. These swings hint at environments or sources with complex magnetic fields or perhaps processes not yet understood. Adding to the complexity is their energy signature. The signals are remarkably powerful, delivering an immense punch in milliseconds. Their brightness temperature indicates unnatural levels challenging known astrophysical sources' limits. Such intense, fleeting bursts suggest extraordinary origins, possibly explosive events or highly efficient energy mechanisms. Yet no known objects like pulsars, quasars, or magnetars produce emissions in this fashion, despite their high energy capabilities. A further enigma is their lack of repetition. Many space signals recur periodically or in bursts, facilitating pattern analysis. These mysterious signals, however, are mainly one-off flashes. Occasionally, similar signals emerge from the same region with slight variations, but their characteristics differ enough to prevent establishing a common source or pattern. Multiple signals sometimes originate nearby, yet their timing, dispersion, and spectral features are inconsistent, making causal links difficult. Their dispersion measure, the extent to which the signal has been slowed by free electrons during transit, poses another puzzle. Normally this helps estimate their distance, but here the measure doesn't match models of intergalactic space's electron content. It hints at environments with unusual electron densities or unknown processes affecting the signals en route. This raises questions about their origins. Are they from distant cosmos, or from local sources within our galaxy, or perhaps terrestrial interference mimicking cosmic signals? These signals stand out not just because of their intensity and spectral oddities, but also their rapid property changes. For example, polarization parameters can change dramatically within milliseconds. Some signals show band limiting, certain frequencies favoured or suppressed. Such rapid modulations suggest environments with extremely strong magnetic fields and swift dynamics, beyond natural sources' typical behaviour. Moreover, some signals exhibit temporal asymmetry, rising rapidly and decaying slowly or vice versa, implying a source with highly dynamic asymmetric conditions. In some cases, a frequency drift occurs during the burst, where the peak intensity shifts across the spectrum within milliseconds. This resembles a chirp, a pattern associated with rapidly changing events like collapsing stars or energetic explosions, but the observed characteristics don't match known explosive phenomena. The idea that these signals aren't natural phenomena has sparked debate. Some hypothesize they could be signs of extraterrestrial technology, signals from alien civilizations attempting to communicate or demonstrate advanced capabilities. The brief but intense bursts, combined with unusual polarization and spectral features, evoke speculative signals from distant intelligences seeking interstellar contact. Others suggest a terrestrial origin, interference from satellites, space debris, or ground-based equipment. However, careful analysis has failed to connect these signals with human-made sources. Their properties don't align with interference patterns, strengthening the case that they are genuine cosmic phenomena from distant, possibly exotic sources yet to be understood. Why would space produce such bizarre signals? They challenge current astrophysical explanations and threaten to overturn existing assumptions. Their peculiar behaviours imply unknown processes, perhaps involving extreme magnetic fields, dense plasma environments, or revolutionary energetic mechanisms. They may indicate a new class of cosmic entities, or even physics beyond the standard model. Scientists are captivated by the possibility that these signals may unlock secrets of the universe's hidden corners. Could they be whispers of an advanced civilization, or traces of an unseen cosmic force? Or are they signs of phenomena so exotic that current science cannot fully grasp them? Their fleeting, puzzling nature pushes the boundaries of human knowledge, prompting efforts to decode fundamental mysteries. The unpredictable polarization swings and spectral anomalies strongly suggest environments with rapidly changing intense magnetic conditions. Their high power levels, despite short durations, imply origins involving extraordinary energy conversion efficiency or explosive events. Yet, their lack of correlation with known astrophysical objects remains perplexing. The frequent absence of repetition contrasts sharply with more common cosmic signals. Their mostly one-time flashes hinder pattern analysis. Occasional similar signals from the same regions have minor differences, preventing confirmation of a common origin. Such variability points to a potentially diverse array of sources or mechanisms, further complicating understanding. The dispersion measure discrepancies hint at unusual signaling pathways or environments. Standard models cannot fully explain the delayed signals, suggesting unknown plasma conditions or intervening media. Clarifying this could help pinpoint their distances and sources, possibly revealing new astrophysical phenomena or environmental conditions. Rapid property shifts, polarization, spectral behavior, intensity occur within milliseconds. Certain features like frequency drift resembling chirps imply rapid changes in source conditions. These observations suggest incredibly dynamic environments, perhaps involving intense magnetic reconnections, plasma instabilities, or energetic transformations that go beyond current models. The asymmetries in temporal profiles, the steep rise followed by slow decay or vice versa, imply non-steady asymmetric processes. Such shapes conflict with simple burst models, indicating complex or evolving source mechanisms. The frequency drifts, sometimes resembling rapidly collapsing systems or explosive events, add further complexity, making pattern recognition difficult. The possibility of artificial origin remains a topic of heated debate. Some theorize these signals are technological, alien attempts at transmission or signaling, based on their intensity, polarization, and spectral features. While speculative, such ideas provoke discussions about extraterrestrial intelligence and the potential for contact. Meanwhile, terrestrial explanations, interference or equipment artifacts are continually examined. Despite thorough analysis, no concrete link to human-made sources has been established. Their characteristics remain inconsistent with known interference, supporting their cosmic origin, yet their exact source remains elusive. The energy involved in some bursts points toward extraordinary processes. Their high brightness, fleeting nature, and spectral properties suggest explosive origins or exotic energy release mechanisms. They challenge existing classification schemes and point toward the possibility of unknown, powerful astrophysical phenomena or even new physics. Understanding these signals could reveal aspects of the universe previously hidden. They might be signatures of advanced alien civilizations, signs of new celestial objects, or manifestations of unknown physical laws. Their elusive nature emphasizes the potential for groundbreaking discoveries, pushing science to its limits. In summary, these signals demonstrate extraordinary behaviors, unpredictable polarization, broad spectral spreads, rapid property changes, and asymmetrical temporal profiles. They defy current explanations, hint at extreme environments, and suggest potentially revolutionary physics. Whether artifacts of distant cosmic processes, signatures of alien intelligence, or indicators of new physical phenomena, they represent an exciting frontier, an enigmatic window into nature's most extreme and mysterious realms. Scientists analyze the data, pondering a tantalizing question. Could this be evidence of something beyond our natural understanding? This question has ignited debates across the astrophysical community, stirring hope, skepticism, and fear. The strange signal exhibits features that, at first glance, seem to whisper of potential artificial origin. One compelling clue is the signal's incredible precision. Natural cosmic phenomena like pulsars or supernova remnants often produce signals with variability and randomness due to chaotic processes. In contrast, this signal is remarkably consistent in its frequency, maintaining a narrow band before fading into cosmic silence. Such spectral stability hints at something deliberately engineered, rather than a fluke of turbulent space matter. The polarization, the orientation of electromagnetic waves, adds to the mystery. Natural sources tend to produce random polarization or patterns linked with known phenomena, such as magnetic fields. But this signal displays an unusually high degree of linear polarization with a consistent orientation throughout brief bursts. It's as if the source had a specific, deliberate alignment, like a cosmic lighthouse aimed precisely at us, then gone dark. Timing and repetition also raise eyebrows. Most natural radio bursts are sporadic, unpredictable, and short-lived. Yet this signal, lasting only a few milliseconds, was detected simultaneously by multiple telescopes across continents. Though the bursts don't follow a known astrophysical cycle, they're clustering hints at an organized or purposeful pattern, almost like a signal designed to attract attention or convey information. Adding to the intrigue, the energy involved appears extraordinary. While natural phenomena can produce intense signals, calculations suggest this burst required an immense and highly concentrated energy source. Some researchers wonder if harnessing such energy would involve advanced technology beyond current capabilities, structures or processes that defy natural explanations. Is this a remnant of an advanced civilization broadcasting across the cosmos, or merely an unknown natural process mimicking intentionality? Then there's the complexity of the signal. Its spectrum reveals fine structure, small variations and modulations on top of the main emission, reminiscent of human encoding methods. This spectral pattern sparks curiosity. Are we witnessing a form of cosmic Morse code? Could an intelligent source be attempting to communicate using modulation patterns similar to ours? Or are these subtle variations natural signatures of exotic phenomena? Some scientists search for signs of deliberate design, patterns, repetitions, symmetrical structures that distinguish artificial signals from natural ones. Interestingly, the bursts show clues of non-randomness. Certain frequencies appear more prominent than chance would produce. This suggests a transmission protocol, a deliberate choice of frequencies, perhaps error-checking sequences similar to human digital communication. Yet skepticism remains. The universe is vast and mysterious, capable of producing phenomena that challenge understanding. Could natural processes, unknown and yet to be discovered, mimic intelligent signals? Are we seeing a cosmic prank, or an extraordinary natural event like magnetic reconnection, or plasma oscillation that current physics cannot explain? When conventional explanations fail, the idea of an artificial origin becomes harder to dismiss. The polarization alignment, spectral narrowness, energy scale, and subtle modulations all suggest the need for new perspectives. It's as if the universe handed us a coded message, one that, if deciphered, might transform our understanding of cosmos and intelligence. This raises profound questions. If the signal is indeed artificial, what does it imply about our place in the universe? Does it suggest we're not alone, part of a larger network of intelligences communicating across cosmic distances? Or is it an artifact left by an ancient civilization, cosmic graffiti? The implications are staggering. Some speculate the features could be an intentionally crafted beacon, designed to engage any detector. For a civilization capable of producing such precise energetic signals, motivations could include seeking contact or asserting their presence. Alternatively, the signal's features might be accidental, natural phenomena mimicking artificial signals with no message behind them. The line between natural and artificial blurs further as new observations emerge. These features compel us to look deeper, question assumptions, and push science's boundaries. They call for developing new tools, new theories, to understand what constitutes intelligence and communication across cosmic distances. Until the true nature of this mysterious signal is uncovered, it remains among the universe's greatest enigmas. Whether from a distant civilization, a natural phenomenon wearing an unnatural mask, or something entirely unforeseen, it confronts us with profound uncertainty and the thrilling possibility that the universe still holds many secrets. The characteristics of this signal, with its precision, polarization, energy, and subtle modulations, suggest it might be artificial, yet no definitive conclusion has been reached. While the features are suggestive of intelligence, they could also be natural phenomena currently beyond our understanding. The scientific community continues to investigate, aware that this signal could redefine human understanding of space, communication, and our cosmic solitude. As research progresses, the significance deepens. The potential for discovering alien technology or natural phenomena with our limited knowledge makes this one of the most exciting puzzles in astrophysics. Every new observation raises questions, and each hypothesis brings us closer to understanding whether we are alone or part of a broader cosmic community. The debate persists: natural chaos or signs of intelligence? The answer remains elusive, but the search itself drives innovation and curiosity. Each feature challenges us to redefine what we consider natural or artificial, routine or extraordinary. Whether a message, a natural coincidence, or something unknown, this signal continues to inspire exploration, pushing our science and imagination to new heights. Ultimately, the investigation of this signal reflects humanity's desire to understand the universe and our place within it. Whether it turns out to be a message from an intelligent species or a natural anomaly, its existence compels us to contemplate profound possibilities. The universe's secrets remain vast, but each discovery, each clue, brings us closer to unraveling the great cosmic puzzle. While evidence hints at artificial features, definitive proof remains elusive. The signal embodies both the mysteries of the cosmos and the potential for extraordinary discovery. It urges us to remain open-minded, innovative, and cautious as we explore the universe's hidden messages. This enigma symbolizes the ongoing human quest for knowledge, an ever-deepening journey into the unknown, where the line between natural phenomena and alien communication continues to blur, fueling the search for cosmic understanding. 767 words. This discovery challenges the very foundations of our understanding of space and matter, compelling scientists to revisit their core assumptions. For decades, our grasp of the universe has relied on the idea that cosmic phenomena follow natural laws governed by physics we have studied and validated. When a signal as strange and intense as this fleeting radio burst appears, it complicates these assumptions, because it doesn't fit neatly into existing frameworks. The burst's intensity and brief duration, lasting mere milliseconds, are extraordinary. It's like capturing a lightning bolt in slow motion. These bursts are among the universe's fastest, most energetic explosions, yet their origins remain largely unknown. The burst observed from a distant galaxy was powerful, displaying spectral features and polarization levels unlike any known natural process. It released more energy than the Sun in a fraction of a second, originating from a galaxy billions of light-years away. This level of energy, combined with the fleeting timing, suggests our models of matter behavior in extreme environments are incomplete, or that some unknown process is at work. Moreover, the spectral features, the specific frequencies and patterns, challenge current understanding. They seem to tell a story no natural phenomenon has previously written. This spectral fingerprint differs from those associated with pulsars, quasars, or other astrophysical objects. It's almost as if the burst carries an encoded message or stems from a physics process we've yet to uncover. The high polarization levels add to the mystery, hinting at a highly organized or structured environment, possibly influenced by intense magnetic fields. These clues imply that the physical conditions needed to produce such a signal are extraordinary, potentially beyond known physics. What makes this even more perplexing is the energy involved. Detecting this burst required our most advanced technologies: global radio telescope arrays, sophisticated data algorithms, and real-time monitoring systems. These instruments are based on our understanding of physics, that space phenomena follow predictable patterns and that such signals are rare and brief. Yet, here was something so atypical that it nearly upended that framework. The implications for our understanding of matter are profound. In physics, matter behaves predictably: solid, liquid, gas, plasma, with specific rules. The burst appears to defy these rules, suggesting that under extreme conditions, matter, or perhaps energy, can manifest in ways our current models don't encompass. Maybe an unknown form of matter driven by intense magnetic or gravitational forces, or an exotic state at the edge of physics is involved. This discovery pushes us to rethink what matter can do under extreme environments. On a larger scale, it raises questions about the universe's structure. The cosmos is filled with dust, gases, plasma, all following predictable behaviors. But if such a phenomenon can produce a burst with these characteristics, what else might be lurking, hidden, or beyond our reach? Could there be other, more exotic phenomena that challenge the very fabric of reality? Are the physical laws we rely on truly universal, or do they have exceptions in certain environments? The discovery also questions the universality of natural laws. Humanity has long believed physics is the same everywhere, but what if some regions of space are so extreme or unique that they give rise to phenomena unlike anything seen on Earth? This broadens our cosmic curiosity into previously dismissed realms, suggesting that the universe may harbour surprises beyond current understanding. A provocative but speculative idea is whether these signals are not purely natural. If an energetic burst displays properties so hard to explain with conventional physics, could it have an artificial origin? Some researchers debate whether these could be signs of advanced extraterrestrial technology, an idea that, while controversial, has gained credibility given the extraordinary nature of these bursts. If true, it would alter our perception of space as a vast, quiet realm filled with natural phenomena alone, and suggest that intelligent civilizations are out there, communicating in ways we're only beginning to understand. This challenge extends beyond physics into philosophy, shaping our cosmic perspective. Are we alone in the universe? Could extraterrestrial civilizations engineer phenomena so extreme as to produce these signals? Might these bursts be deliberate messages or beacons? Or are they remnants of civilizations long gone, ancient technologies or alien constructs? The possibility of artificial origins compels us to reconsider what intelligence might look like elsewhere, and how such civilizations could manipulate space and matter. Beyond these questions, the discovery underscores how much remains to be uncovered in the universe's tapestry. It encourages the development of new theories to explain phenomena outside current models. Whether these bursts are natural but unexplained or messages from extraterrestrial intelligence, they serve as stark reminders of the universe's secrets, mysteries that challenge our understanding of space, matter, and the laws governing everything. This isn't just new data. It's an opening to possibilities we hadn't fully considered. It forces scientists to question what they believe about the universe's workings, igniting curiosity for further exploration, pushing beyond current understanding to seek answers we didn't realize we had. The universe still holds many surprises waiting to reshape our view of space and matter, possibly redefining our place in the cosmos. In essence, the finding pushes the boundaries of science and technology, urging new theories for anomalous phenomena. Whether natural or intelligent in origin, these bursts remind us that the universe still hides many secrets. They challenge our understanding of fundamental physics and the cosmos, suggesting we only grasp a fraction of what truly exists. The universe, it seems, still offers mysteries that could change everything we know about space, matter, and our place within it. This discovery is a wake-up call, highlighting gaps in our knowledge and inspiring a deeper quest for understanding cosmic truths. It compels the scientific community to rethink assumptions about natural laws, pushing us to develop new frameworks to incorporate phenomena beyond our current explanations. Whether these signals are natural anomalies or signs of extraterrestrial intelligence, they emphasize the universe's complexity and mystery. As we continue exploring, we may find that the universe holds even more extraordinary surprises, capable of expanding or overturning our worldview. Scientists investigating this bizarre burst are turning their attention to dark matter and dark energy, which together make up about 96% of the universe, but remain deeply mysterious. When such an energetic signal appears from a distant galaxy, one that defies current understanding, it prompts a re-evaluation of how these unseen components might be involved or affected. Dark matter, constituting roughly 25% of the universe's mass energy, is mainly inferred through its gravitational effects on visible matter, light, and large-scale structures. It acts as a cosmic scaffold, shaping galaxy formation and clusters. Prevailing theories suggest dark matter consists of weakly interacting massive particles, WIMPs, axions, or other exotic particles that weakly interact with electromagnetic radiation, making direct detection difficult. If the signal is connected to dark matter via natural or artificial processes, it suggests our understanding is incomplete. Some hypotheses propose dark matter. Particles can annihilate or decay, releasing high-energy photons or other particles. Such annihilations might produce bursts of radio waves or other signals. An energetic fast radio burst, FRB, with unusual spectral features could hint at dark matter interactions previously only theorized. These possibilities suggest dark matter may not simply be a passive gravitational component but an active participant influencing astrophysical phenomena. For example, dark matter might accumulate in neutron star or black hole cores, altering their behavior or triggering explosive events. If linked to such interactions, it indicates dark matter plays a more dynamic role in cosmic evolution. The burst's unusual polarization features make certain dark matter models especially intriguing. Axions, one dark matter candidate, are hypothesized to weakly couple to photons and might convert into radio waves when interacting with magnetic fields. Such axion-photon conversions could produce transient signals like this burst, offering insights into dark matter's nature and interactions. Turning to dark energy, which makes up about 71% of the universe's energy, its influence might be indirect yet significant. Dark energy drives the universe's accelerated expansion, a discovery awarded the Nobel Prize. Its nature remains speculative. Some see it as a cosmological constant, others propose a dynamic field called quintessence. The effect of this space signal on dark energy theories may seem subtle, but remains crucial. Some models propose dark energy could vary over time or space, possibly affected by dark matter interactions. These interactions might subtly influence cosmic structure formation, galaxy evolution, and gravitational phenomena. If the burst indicates that dark matter interacts more strongly with electromagnetic sectors or reveals undiscovered particles or fields, it challenges the presumed constancy of dark energy. The energy released might be linked to a local fluctuation or an exotic phase transition in the dark sector, temporarily altering dark energy's behavior locally. Such phenomena could influence galaxy evolution and the universe's expansion dynamics, suggesting current models might be incomplete. Moreover, if the burst involves ultra-energetic processes with unknown particles, it could inspire theories unifying dark matter and dark energy within a single framework. Some models posit both as aspects of a single underlying field or entity, an idea gaining plausibility given their dominance yet mysterious natures. If the signal is a messenger from beyond current understanding, it might hint at physics bridging dark matter and dark energy, leading toward a more comprehensive cosmic theory. Other hypotheses suggest that the universe's acceleration might be driven by exotic effects, like modifications to Einstein's general relativity. These theories propose that what we interpret as dark energy could be a consequence of altered gravity at cosmic scales. If the signal reflects phenomena related to these larger-scale modifications, it could provide empirical clues to refine such models. Essentially, this fleeting signal might be a signpost toward a new understanding of spacetime's fabric. Ultimately, these unusual observations act as cosmic firecrackers, igniting debates about the fundamental makeup of reality. They push us to expand models, explore interactions among particles and forces, and consider new physics. Dark matter and dark energy, once invoked primarily to explain observations, are now seen as central to understanding phenomena once thought disconnected. As data pours in from telescopes, arrays, and simulations, researchers confront pressing questions. Could this indicate dark matter is more interactive? Might dark energy itself be dynamic, capable of flickering or changing in response to events? Could extraterrestrial intelligence harness or produce such signals? Or do these observations herald a new paradigm, one where the universe's unseen components are woven into its very fabric? Whatever the case, this burst is more than an anomaly. It's a cosmic puzzle urging deeper exploration into the universe's profound mysteries. It challenges us to look beyond the visible, to understand invisible forces shaping our cosmos, and potentially to redefine our understanding of its fundamental nature. These observations compel us to reconsider the very fabric of space-time, to search for new particles, interactions, and fields that might unify cosmology and quantum physics. In the end, the key question remains: what lies behind these mysterious signals? Are they signs of hidden particles or forces, or do they reveal a new aspect of cosmology we have yet to grasp? As scientists examine the data, refine theories, and develop new experiments, the hope is that this unusual burst will shed light on the unseen universe, illuminating the dark matter and dark energy that dominate our cosmos. Continued investigation may uncover evidence that these phenomena are connected to fundamental physics yet to be understood. The findings could transform current models, pushing us toward a deeper comprehension of the universe's composition, evolution, and underlying laws. This is a moment of profound scientific potential, where one extraordinary signal could revolutionize our understanding of the cosmos, unlocking secrets hidden in the darkness that pervades all of space. Could this object be evidence of phenomena beyond known physics? It's a question that challenges every scientist pondering this enigma. The universe remains our greatest puzzle, full of mysteries that ignite curiosity, challenge assumptions, and push the boundaries of possibility. When faced with something extraordinary like this, the idea that it might point toward physics beyond our current understanding is both thrilling and unsettling. The discovery is astonishing. The fleeting radio burst, unlike anything catalogued, shined with such intensity it momentarily outshone the entire galaxy it originated from. Its spectral features defied norms, not fitting typical patterns like pulsars or supernovae. The high polarization suggested an ordered magnetic field or an exotic process at work. Its energy levels exceeded expectations based on standard models, hinting at something potentially revolutionary. Could these deviations be due to a new class of objects or processes? In astrophysics, models based on Einstein's relativity, quantum mechanics, and plasma physics have served well, but are always subject to testing and refinement. The burst's peculiarities raise fundamental questions. The high polarization and rapid fluctuations imply environments with incredibly intense magnetic fields, perhaps exceeding those of magnetars or pulsars. But what if conditions are even more extreme, beyond what current physics can explain? The energy release mechanisms might involve exotic matter or unknown states of physical laws. One provocative possibility involves phenomena related to quantum gravity or unified theories of fundamental forces. These predict subtle effects in space-time that could appear under extreme conditions, near black holes or neutron stars, or cosmic catastrophes. If the burst's properties align with such predictions, it could suggest the involved object is a portal to understanding physics at the Planck scale, where space-time might behave in ways beyond current comprehension. Another tantalizing but speculative idea concerns technological activity, perhaps an artifact of an intelligent civilization beyond Earth. The enormous energy levels and spectral patterns have led some to consider this might be an alien transmission or a deliberately engineered signal designed to be detectable across cosmic distances. If true, it challenges our assumptions about extraterrestrial life and compels us to reconsider what constitutes evidence of advanced civilizations. Beyond extraterrestrial technology, the larger question persists. Are we witnessing phenomena that defy natural laws? Some theories propose the existence of exotic astrophysical objects, quark stars, strange matter, or even more speculative entities like wormholes or signals from higher dimensions. These once purely theoretical ideas are gaining credibility through observations like this. The burst could originate from processes involving violations of known physical laws, localized breakdowns of relativity or quantum mechanics under extreme conditions. Such an event would revolutionize physics, exposing limitations and inspiring new models that better describe reality. It might mark the dawn of a new era, unlocking cosmic secrets and revealing a universe richer and more mysterious than imagined. Furthermore, this potential evidence urges reflection on scientific progress. Breakthroughs often come from anomalies, observations that challenge and expand understanding. Discoveries like nuclear physics, cosmic rays, and gravitational waves were initially dismissed or considered impossible, until advances in technology and curiosity pushed boundaries. Perhaps we're on the brink of a paradigm shift. Some aspects of the burst seem so counterintuitive they suggest unknown physics. For example, the rapid temporal fluctuations imply processes on timescales difficult to reconcile with current physics, unless exotic states of matter or unknown fields are involved. Its high energy density, concentrated briefly, hints at mechanisms or efficiencies not aligned with known sources. Could nature have uncovered shortcuts, phenomena classical physics cannot yet explain, similar to how quantum mechanics expanded our understanding microscopically? In any case, this discovery underscores how much of the universe remains hidden behind mysteries that challenge physics' foundations. Whether the answer involves novel astrophysical phenomena, exotic matter, or signs of extraterrestrial technology, it's clear we're on the cusp of a paradigm shift. Science advances through the unknown and the unexplained. Each anomaly prompts further investigation, questions assumptions, and broadens frameworks. Perhaps this strange radio burst is a message from the cosmos, a relic of an unknown process, or a sign of discoveries that will transform our grasp of reality. The universe surprises us, shakes our knowledge pillars, and urges us to look beyond what we think we know. Our task now is to scrutinize, test, and imagine boldly. These observations might be the first signs of physics beyond current boundaries, leading to a new era of discovery, unlocking secrets as old as time and as vast as the cosmos. The potential implications are profound. If confirmed as evidence beyond known physics, this detection could revolutionize our understanding of universal laws. It might unveil new states of matter, unseen forces, or dimensions. We could encounter phenomena challenging the fabric of space-time, revealing cracks in current theories and paving the way for a unified understanding of nature's fundamental workings. This discovery could become a cornerstone for new physics, guiding us toward a more complete picture of reality. It might also point to exotic objects, quark stars, strange matter, or entities like wormholes, initially theoretical but now approaching validation through observations like this. The burst's mysterious qualities could hint at processes involving physics beyond our models, violations or modifications of relativity, quantum mechanics, or field theories at high energies. These phenomena extend current science, challenging us to consider new laws or mechanisms. The idea that this might be an artifact or sign of an alien civilization adds another layer. Should technological activity be involved, a deliberate signal or engineered transmission, this would reshape assumptions about life and intelligence in the universe. It suggests that advanced civilizations might produce detectable signals, opening new avenues in SETI and cosmic exploration. In summary, this discovery exemplifies how much remains unknown, and how anomalies can catalyze revolutions. Whether tied to novel astrophysical phenomena, exotic matter, or extraterrestrial intelligence, it deserves rigorous investigation. It may herald new physics, or simply be a baffling but explainable event. Its implications are immense. History shows science flourishes at the edge of the unknown. Every anomaly offers an opportunity, a challenge to refine or rethink existing theories. Whether this burst reveals a new physical principle, exhibits exotic matter, or signals technological activity, it reminds us that the universe is more mysterious than current models suggest. Its secrets await discovery, promising an era of profound transformation in understanding reality. The universe's surprises compel us to explore further, to question, to test, and to open our minds to astonishing possibilities beyond current knowledge. Scientists worldwide are racing to understand what caused this extraordinary signal. There's no simple answer, a neat formula fitting this cosmic puzzle. Instead, various models, some based on established physics and others more speculative, compete to explain this bizarre fast radio burst, FRB. Each offers a different perspective on what might be happening deep within the distant galaxy where the event occurred. Exploring these possibilities opens new frontiers for understanding the universe itself. A traditional explanation traces back to the life cycle of massive stars. When giant stars exhaust their fuel, they sometimes explode as supernovae, collapsing into neutron stars, dense objects with city-sized volumes and intense gravitational and magnetic fields. Among neutron stars are magnetars, which can produce intense bursts of radio waves. Magnetars have magnetic fields trillions of times stronger than Earth's, and their magnetic activity is known to cause energetic outbursts. The peculiar spectral features and high polarization of this burst could, in theory, result from magnetar flares, where magnetic reconnection events unleash powerful emissions. However, this model struggles to fully explain the burst's extraordinary intensity and fleeting nature at such distances. The spectral signatures might suggest exotic processes on the star's surface, but the energy requirements make magnetars insufficient explanations on their own. These objects usually produce repeated, less intense pulses, not a solitary intense flash like this. Another approach involves the environment around black holes. Accretion disks, gases and dust spiraling into black holes are known to generate powerful electromagnetic emissions. If instabilities or magnetic interactions occur within these disks, they could produce radio bursts of significant magnitude. This aligns with the idea that the burst could originate near an active galactic nucleus, perhaps linked to a supermassive black hole experiencing magnetic turbulence. Yet, the spectral features and brief, one-off nature complicate this explanation. Black hole accretion events are typically longer-lasting or recurrent, with complex emission profiles. The polarization signature also suggests a structured magnetic environment, not always seen around black holes. Still, further investigation into this possibility is warranted, especially if more similar bursts are detected from galactic centers. Some scientists consider particle physics and hypothetical objects like strange or quark stars, extremely dense stars made of exotic matter. A sudden starquake or destabilization could release enormous energy, fitting the burst profile. This idea is intriguing because it touches on unresolved questions about matter under extreme conditions, potentially revealing physics beyond current capabilities. However, these models remain speculative. No confirmed evidence supports strange or quark stars producing such FRBs. Still, the spectral features hint at highly energetic, magnetic-driven processes happening inside a compact object, leaving this possibility open. Another idea involves catastrophic events, like neutron star mergers, or a neutron star fragmenting and ejecting material at near-light speeds. Such violent mergers produce gravitational waves and electromagnetic signals, as previously observed. The burst could be a snapshot of such an event occurring in a distant galaxy. But these mergers typically produce multiple signals or afterglows over longer periods. The burst polarization and singularity don't fit perfectly with typical merger profiles. Still, they remain plausible if the event was a variation of known violent processes. One of the most provocative hypotheses posits an artificially engineered source, an alien civilization deliberately broadcasting a signal or beacon. The spectral features, high polarization, and energy levels could signal advanced technological activity, perhaps a deliberate message or cosmic beacon designed to attract attention. Skeptics argue invoking intelligent origins is extraordinary and require overwhelming evidence, so natural explanations should be exhausted first. Yet the burst's features, its polarization, sudden appearance, and spectral anomalies resemble science fiction notions of artificial sources, collimated beams, encoded signals, patterned emissions meant for detection across vast distances. Some theorists even consider the most speculative idea, that the burst may be an entirely new class of astrophysical phenomenon, unknown to science. It might be a manifestation of an unprecedented process, something current understanding has yet to encounter. This acknowledges that the universe often surprises us, and as observation techniques improve, new phenomena could challenge existing theories and expand our knowledge. Each model, from the well-supported to highly speculative, drives efforts to solve this cosmic mystery. They embody our push beyond current knowledge, exploring space's darkness and illuminating the unknown. Whether the answer lies within known physical laws or in entirely new physics, this burst is already rewriting textbooks, urging scientists to look deeper and think bigger. The universe whispers secrets, and we are just beginning to listen. The potential explanations span from familiar astrophysical processes like magnetar flares and black hole environments to more exotic ideas involving quark stars or extraterrestrial intelligence. As data accumulates, these models will be tested, refined, or discarded, narrowing the possibilities. This burst challenges our understanding, highlighting the limits of current theories and the potential for discovery. The possibility that it could be a new phenomenon or a sign of extraterrestrial life fuels curiosity and debate. The search for answers continues, driven by advances in observational technology and theoretical insight. Each discovery, each new data point, brings us closer to understanding whether this signal is a natural cosmic event, an artifact of extreme astrophysics, or something entirely unforeseen. In the end, these models reflect our desire to comprehend and explore the universe's deepest mysteries. No matter the outcome, this cosmic mystery emphasizes curiosity, persistence, and the human need to listen to the universe's secrets and understand our place within it. The story of this burst is just beginning, yet it already marks a turning point in astrophysics, hinting at discoveries yet to come and the ongoing adventure of cosmic exploration. What are we truly looking at here? Is this shimmering enigma a product of natural cosmic processes so extraordinary they exceed our understanding? Or does it hint at something more deliberate? Perhaps an artifact of intelligent life beyond our world? Scientists struggle with this puzzle. The debate rages on, fueled by tantalizing clues and baffling anomalies. Let's explore both possibilities. Cosmic phenomena often surprise us. The universe is a grand laboratory, constantly producing events that challenge our theories. Consider fast radio bursts, brief, intense radio flashes from billions of light years away that baffled scientists until natural origins were proposed. Perhaps this object, with its brightness, unusual polarization, and fleeting nature, is another chapter in the universe's natural wonders. What natural scenarios could produce such a potent burst? Hypotheses involve magnetars, highly magnetized neutron stars, that can unleash colossal energy during starquakes or magnetic reconfigurations. Could this object be a magnetar in an unrecognized phase, emitting an unprecedented burst with features we don't yet understand? Alternatively, interactions involving black holes or exotic plasma phenomena in distant galaxies could produce these rare radio flashes. These events, while extraordinary, are still rooted in natural physics, extended by cosmic forces beyond our current knowledge. However, peculiar specifics cannot be ignored. The spectral peculiarities and polarization patterns suggest something fundamentally unusual. Some argue natural sources should produce signals with predictable properties based on known mechanisms. When signals deviate from models, like this one, they open the door to more exotic explanations. What about the possibility that this indicates intelligence? At first, it seems startling, claiming a sign of communication or a signature left by extraterrestrial civilization. Yet history shows the universe sometimes hints at the unknown in mysterious ways. The famous WOW signal detected decades ago was a strong radio transient that remains unexplained, sparking speculation about an intelligent origin. Could this current discovery be a more subtle form of communication, a beacon or message indicating presence? Proponents of this idea point to the object's properties: coherence, polarization, and intensity, all potentially consistent with an engineered signal rather than a natural event. Its singular, bright nature might imply a deliberate effort to attract attention, or a signature designed to stand out across cosmic distances. Similar to how humans use radio signals and laser beacons to reach out, brightness combined with subtlety could be intended to be detected by a distant recipient. But skeptics raise questions. If extraterrestrial civilizations can produce such signals, why haven't we detected similar ones elsewhere? Are we missing larger patterns, or is this a one-time anomaly? If an artificial signal, it might be highly targeted, aimed directly at us or a specific location we happen to observe. The absence of other signals casts doubt and advises caution. Scientists are deploying every tool available: radio telescopes to analyze detailed structure, polarization, dispersion, and other properties. This meticulous analysis could reveal signs of intentional modulation, prime number patterns or embedded signals, or simply natural chaos. If artificial, certain hallmarks might be present, indicating deliberate engineering rather than natural randomness. But perhaps we're missing the bigger picture. It's possible that what we observe is a new class of natural phenomenon, something that does not fit existing categories, Just as pulsars revealed a new type of neutron star, this could be a new astrophysical process requiring us to rethink cosmic physics. Maybe it's a rare configuration of known objects or an exotic plasma process under conditions in the early universe. Ultimately, the likelihood hinges on the data. The more clues gathered, the clearer the picture becomes. So far, evidence does not conclusively favour natural or artificial origins. Its properties are extraordinary, pushing the boundaries of known phenomena, yet they do not rule out a natural explanation. That ambiguity fuels excitement and suspense. What makes this discovery compelling is not just the anomaly, but what it signifies: a bright beacon into the unknown. If natural, it could lead to new physics or cosmic understanding. If artificial, it might represent contact, a message from beyond, a whisper of intelligence amid the vast dark expanse. Until further data arrives, the question remains open. Its true nature might be more complex than it appears, possibly a hybrid, or something entirely unforeseen. The universe's ingenuity means every answer deepens the mystery, inviting us to think broadly, look farther, and remain humble. Monitoring this source and others like it, we hope to find the keys to understanding whether we are truly alone or part of a universe teeming with intelligent life. Could this otherworldly signal truly be a natural phenomenon hidden within cosmic dust and darkness? Or does it hint at something entirely different, a sign of intelligence beyond our own? The possibilities proposed by scientists span a wide spectrum, stirring excitement and debate in the astronomical community. Here we explore leading ideas about the origin of this strange burst and its implications for our universe. Some scientists consider the simplest explanation. It might be a rare or unknown natural astrophysical event. The universe harbours many enigmas that remain elusive despite centuries of study. Certain models suggest these bursts originate from highly energetic processes involving neutron stars, black hole accretion disks, or exotic objects like magnetars, neutron stars with immensely powerful magnetic fields. These cosmic powerhouses emit intense radiation, and under specific conditions could produce bursts brighter and more brief than anything observed before. However, this signal's unique spectral properties and polarization stretch known phenomana's limits. Its rapid profile and extraordinary intensity aren't easily explained by traditional models. Could it be a new type of gamma-ray burst, perhaps from processes in the death throes of massive stars or collapsing neutron stars? Or might it involve interactions with dark matter or hypothetical particles beyond our detection? These hypotheses push the boundaries of physics. Another idea suggests the signal might originate from an unknown class of astrophysical objects. Imagine some cosmic entity or structure that doesn't fit current taxonomy, but could generate such bursts under certain conditions. Could we be witnessing a new celestial phenomenon, perhaps linked to strange stars or hypercompact objects challenging matter's extremes? Perhaps the bursts result from cosmic feedback processes yet to be understood, revealing a novel energy release mechanism in the universe. Some scientists speculate the signal could originate near black holes. The chaotic environments and interactions in these regions could produce energetic radio emissions, magnetic reconnection events, akin to solar flares but vastly more energetic, in accretion disks of supermassive black holes might generate intense, unpredictable bursts. Yet, the spectral signatures don't fully match typical emissions from such regions, indicating more complex causes may be involved. The most tantalizing and controversial speculation involves the possibility of artificial origin. Could this be the first evidence of extraterrestrial intelligence attempting to communicate? The idea is provocative, especially given the burst's anomalous features. Its intensity, polarization, and fleeting nature resemble signals a technologically advanced society might deliberately craft, perhaps as a beacon or test, radiating signals across the cosmos. Many scientists urge caution, emphasizing the importance of ruling out natural explanations first. Still, the peculiar nature of this burst invites such speculation. Could it be a remnant of alien technology, like a cosmic lighthouse meant to be detected? Or an artifact of an unknown process, an artificial phenomenon embedded within space itself, crafted with intent beyond current understanding? There are also more speculative ideas involving extraterrestrial artifacts or megastructures, projects harnessing star energy or manipulating space-time. Imagine a civilization building structures like Dyson spheres, which when interacting with their surroundings produce unusual emissions. If true, we could be witnessing signals from an alien civilization's endeavours, broadcasted across the galaxy in ways we are only beginning to interpret. Another debated idea involves techno-signatures, signals or anomalies from alien technologies rather than natural sources. For this burst, scientists wonder whether it might resemble a radar pulse or a deliberate beacon, designed to stand out against the cosmic background. Such a scenario raises profound questions about intelligence and the potential for civilizations to communicate over interstellar distances. Further possibilities involve natural phenomena so rare and extreme they blur with artificial causes. For example, some hypothesize stellar earthquakes, massive starquakes, that, under extreme conditions, emit localized radio bursts. Others wonder if the universe itself holds undiscovered physics or particles. Could this be a manifestation of higher dimensions, a flickering of forces beyond our perception, defying natural laws? Each explanation carries uncertainties. Validating these hypotheses requires additional observations. Is this a one-time fluke or part of a pattern? Will future detections reveal more signals? Could other telescopes better pinpoint the source? The search continues, with each detection potentially shifting understanding, testing theories, and refining models. What's certain is that such a discovery pushes us to confront our knowledge limits. Whether natural or artificial, the burst's origin raises questions about the universe's complexity and the potential for other intelligences lurking in space. It challenges our assumptions, urging deeper exploration into space and cosmic history, and makes us wonder if we are truly alone or part of a universe far more mysterious than imagined. This intriguing signal underscores the need for continued observation and analysis. As technology advances, our ability to detect and interpret such phenomena improves, opening new windows into the universe's hidden facets. Each new burst or anomaly adds a piece to the puzzle, enriching our understanding and fueling the quest to determine whether we're alone. The universe's vastness and complexity suggest many mysteries remain, waiting to be uncovered. Whether these signals are natural or artificial, they remind us that the cosmos holds secrets beyond our current grasp, encouraging us to keep searching, questioning, and exploring for answers that might redefine our position in the universe. 786 words. Could this enigmatic burst be a relic from a long-past celestial event? It's tempting to think that what we observe might not stem from active current processes, but rather from an echo of something that happened eons ago, a cosmic fossil whispering across space and time. To consider this, we need to explore what kinds of ancient astrophysical phenomena could leave such an unusual signature. One candidate is a massive explosion, perhaps a supernova in its final moments, or an exotic event like a gamma ray burst from a distant galaxy. These phenomena release immense energy, producing intense bursts of radiation that might linger. However, the characteristics of this recent detection don't align with typical supernova remnants or gamma ray afterglows. Its spectral features and polarization suggest a different origin, potentially more subtle than a straightforward explosion. Another possibility involves the aftermath of neutron star collisions, or their interactions with black holes. Such cosmic collisions generate gravitational waves, gamma-ray flashes, and radio remnants that can persist. Yet, the fleeting nature and properties of the signal imply we're not witnessing the late stages of a collision's aftermath. Instead, it appears to be a ghost, a residual imprint rather than direct emission from violent activity. The idea of ancient active galactic nuclei or quasars also arises. These supermassive black holes emit jets of particles and radiation that persist for millions of years, fading gradually. We might be observing a relic jet, an aged remnant of a once active galaxy core. Such remnants can produce faint polarized radio emissions lingering long after core activity ceases. Still, the brightness and bursty nature challenge that explanation, too transient and peculiar to be a simple relic of a dying jet. Could this be a remnant of a cosmic event that once lit up vast regions, leaving behind a pattern like a cosmic scar? Imagine a star's death, or energetic interactions creating plasma filaments or magnetic structures unravelling over cosmic epochs. Such remnants might still produce detectable signals, although rarely and unpredictably. They could be faint, ghostly signatures of events that reshaped galactic environments long ago. Further, primordial black holes, or relics from the universe's early phases could be involved. If such objects existed, they might have interacted with matter eons ago, leaving subtle clues. What we're seeing might be an anomaly, an ancient footprint of a distant primordial event so deep in history that it defies straightforward interpretation. Such findings could offer insights into early universe processes or galaxy evolution spanning billions of years. But we should also consider that the signal isn't a remnant, but caused by less understood processes. Could it be due to rare, natural phenomena only now detectable? Phenomena hidden until recent technological advances revealed them. Sometimes the universe surprises us with phenomena not linked to classical events, but to new physics, resonances in magnetic fields, exotic particle interactions, or effects involving dark matter or dark energy. Though seemingly far-fetched, these ideas are plausible given the universe's complexity. Another perspective is that some cosmic metaphors, structures or phenomena with prolonged lifespans, might be responsible. Some cosmic events could leave long-lasting ripples, whispering from the distant past and drifting across space over eons. They could stem from catastrophic events that subtly alter matter and fields, creating semi-stable structures that only flare under certain conditions. These might be silent witnesses to epochs beyond our horizon, appearing as faint signals from long ago. If it is a remnant, questions arise. How has it survived so long? How have its properties evolved over billions of years? Why does it manifest as a brief burst rather than continuous emission? The nature of this signal suggests a complex interplay of factors. Might it be part of a larger puzzle? A fragment of cosmic history, fragmented over cosmic timescales? Could recent nearby events re-energize such relics? Like treasure buried and resurfaced by tectonic shifts, perhaps cosmic structures are stirred into activity by recent events, shock waves or magnetic disturbances driven by galaxy processes. Ultimately, considering this as a remnant of an ancient event is alluring, but it prompts many questions about cosmic history. If true, we are viewing a snapshot from the universe's past, a frozen moment waiting to be decoded. It might be the universe's whisper of its secrets, stories etched in faint radio echoes from cosmic giants long gone. Recognizing and understanding such remnants could reshape our perception of cosmic life cycle, revealing that age doesn't always mean disappearance. Some remnants linger long after their origins fade into the background. This serves as a reminder that in the grand cosmic narrative, the past isn't always silent. The universe sometimes leaves behind faint ghostly signatures, waiting for us to notice, interpret, and unravel what they reveal about its billion-year history. The moment the signal was detected, numerous questions flooded the minds of astronomers and scientists worldwide. Was this just another cosmic coincidence? Or could it be something more, something indicating intelligence beyond our own? As they analysed the data, initial excitement was met with cautious skepticism. Amid the myriad possibilities, a few intriguing indicators, some subtle, others startling, began to stand out, fueling the debate. One compelling aspect scrutinised was the signal's brightness and brevity. The burst, a radio flash lasting mere milliseconds, was extraordinary given its distant origin. To produce such a sharp, powerful, short-lived signal suggests a natural process of immense energy. Yet the event's clarity raises questions. Could such a precise, focused energy release be the work of an intelligent entity employing advanced technology? The spectral structure of the signal added to the intrigue. Its frequency distribution was not typical of natural astrophysical phenomena. Most cosmic signals tend to spread or drift predictably, influenced by their transit. This burst, however, displayed an unusually narrow and finely tuned spectral pattern. Some scientists argue that natural processes are unlikely to produce such narrow frequency bands, more reminiscent of signals deliberately engineered or modulated. This pattern resembled what an advanced civilization might transmit as a beacon or informational signal. Further questioning arose from the polarization of the burst. Radio waves passing through magnetic fields exhibit characteristic polarization signatures, which are usually predictable. But this burst polarization was highly unusual, intense, stable, and not easily explained by known natural mechanisms. Could this be a mark of technological activity or communication, deliberately crafted to stand out? Alternatively, might it be an artificially embedded watermark, designed to be unmistakably artificial? its energetic profile complicated matters further. The burst emitted an energy comparable to a star's entire internal energy in a fraction of a second. Typical sources with such energy, like supernovae or neutron star mergers, usually have observable counterparts, yet no such phenomena or gravitational waves were detected. Its isolated nature fueled speculation. Could it be a controlled release, a signal mimicking natural chaos but with an underlying pattern understandable by an advanced civilization? Scientists also considered the broader context of the origin. The galaxy where the burst originated was distant but not so far that signs of previous technological civilizations would be impossible to detect. Might this burst be part of a larger pattern, perhaps a deliberate sequence, a mode of interstellar communication? Could it be an attempt by an intelligent species to contact across space, like a lighthouse signaling in the night? Some of the more speculative indicators focused on the signal's implications. Notably, the emission frequency coincided with a quiet window in the spectrum, a band less crowded with natural cosmic signals. This quiet corridor could be a deliberate choice, allowing an intentionally crafted signal to pass unnoticed by background noise. Such frequency selection might be an attempt to ensure detectability without interference. Mathematicians and information theorists suggest that certain patterns, like sequences based on prime numbers, mathematical constants, or universal symbols, are unlikely to occur randomly. Analysing this burst's spectral and temporal structure, some see subtle hints of such universal coding, potentially encrypted or designed signalling. Though highly speculative, this raises the possibility that some features were intentionally included, meant to be recognised by other intelligent beings familiar with similar codes. However, caution remains essential. Natural astrophysical phenomena are diverse and often deceptive. Magnetic star activity, plasma interactions, or exotic physics could produce signals that appear anomalous but are naturally occurring. The universe might hold surprises that mimic signals of intelligence, yet this doesn't dismiss the possibility that we may be witnessing a faint whisper of extraterrestrial intelligence, a cosmic message prompting us to listen more carefully. The technological capacity needed to produce such a burst suggests a level of sophistication far beyond current human ability. Reproducing these signals would require advanced energy control and engineering, indicating the potential presence of an intelligent civilization at the galaxy's edge. If such beings exist, these signals may represent some of their earliest attempts at communication or signals to announce their presence. In a universe teeming with potential life, these events might be the first glimpses of something extraordinary. Nonetheless, uncertainty persists. Could these signals be natural phenomena as yet poorly understood? Could plasma instabilities or exotic astrophysics produce similar signals? Or is the universe as silent and lonely as it often appears, hiding an unseen community of intelligent beings attempting to contact us? The core question remains: are these indicators clues pointing to an intelligent origin, or just cosmic coincidences? It's a tantalizing challenge, pushing science to not only seek answers, but to broaden its understanding of what natural phenomena versus signs of intent entail. With each detection, we edge closer to an answer, redefining our understanding of our place in the universe and the possibility of extraterrestrial intelligence. The response from the scientific community has been electrifying. News of the mysterious signal spread rapidly through academic circles and beyond, sparking excitement and apprehension. Researchers worldwide mobilized, dedicating resources and ingenuity to decipher its significance. Debates erupted on online forums, in university halls, and major research institutions, everyone eager to offer hypotheses, challenge assumptions, and interpret the data. Astronomers led the charge, utilizing the most advanced radio telescopes and observational strategies. They worked tirelessly, coordinating global efforts to monitor the source continuously, aiming to catch the signal again or detect similar phenomena. The initial detection was fleeting, a burst lasting just milliseconds before vanishing into space. This brevity deepened the mystery, prompting follow-up observations to capture more data. Automated alert systems were employed to respond swiftly to transient signals, striving to document each nuance of these enigmatic bursts. Physicists approached the data through different lenses, analysing spectral peculiarities and polarization anomalies. The signal's spectral profile did not match known cosmic sources, sparking theories from exotic, highly magnetized objects to entirely new astrophysical phenomena. Many remained cautious, unwilling to dismiss the possibility of an artificial origin. SETI, Search for Extraterrestrial Intelligence, researchers expressed both cautious hope and skepticism, emphasizing that extraordinary claims require extraordinary evidence. The very nature of the signal invigorated searches for phenomena beyond current physics, sparking discussions about potential new laws or mechanisms. Institutions responded by allocating additional funding and forming dedicated task forces. Agencies like NASA, the European Space Agency, and national science bodies funded rapid response projects to analyze the data. Some teams employed machine learning algorithms to sift through vast datasets, identifying patterns too subtle for manual analysis. Others developed theoretical models to explain the signals, considering radical hypotheses such as communication beams from advanced civilizations or alien artifacts interacting with cosmic processes. The intellectual atmosphere was a mix of skepticism and curiosity. Leading astrophysicists acknowledged that their understanding of extreme and bizarre phenomena is limited. Many called for humility, reminding others that the universe often surprises even its most seasoned explorers. They stressed thorough analysis and verification before jumping to conclusions. Nonetheless, each new observation raised questions, fueling ongoing investigation. In broader scientific debates, discussions centered on what constitutes convincing evidence of non-natural origins. Some argued that the spectral features and rapid polarization swings might be signs of unknown astrophysical objects, perhaps a new class of neutron stars, black holes, or novel states of matter. Others suggested that the signals could result from cosmic glitches or interference from phenomena beyond current understanding, rather than artificial sources. The implications of this discovery have also been hotly debated. If the signals are artificial, humanity's place in the universe could be forever altered. Such a revelation would impact philosophy, theology, and our self-perception. Conversations about what it means to be alone in the cosmos accelerated. Should we investigate further or proceed cautiously? Could this be a single anomaly, or the start of a new era of exploration and discovery? Some physicists revisited foundational theories, exploring electromagnetic propagation, quantum phenomena, and potential modifications to relativity capable of explaining these signals. Others entertained more speculative ideas, suggesting perhaps the signals are remnants of cosmic experiments or leaks from unknown natural processes that mimic intelligence. International collaborations intensified, with data and theories shared across borders as part of a collective effort to decode this cosmic message. Multidisciplinary teams, combining astronomers, physicists, information scientists, and anthropologists, explored nearly every angle. The atmosphere was charged with urgency but tempered by cautious optimism. Many acknowledged that history's greatest discoveries often arise from perplexing problems, and this was no exception. The pursuit of answers continues with perseverance. Public response matched that of the scientific community. Media outlets echoed excitement, with some sensationalizing potential alien contact scenarios and others emphasizing strict scientific rigor. Governments issued cautious statements supporting ongoing research and urging restraint. Space agencies hinted at future missions and upgrades to observatories, preparing for the possibility that the signals might reappear, offering new opportunities for study. It's too early for firm conclusions, yet the collective response underscores that humanity stands at a pivotal moment. We are peering into the unknown, wielding technology and curiosity to unlock secrets of the universe. The thrill of the hunt drives us, even as profound questions remain. This discovery serves as a reminder of how much remains beyond our understanding, about the cosmos and ourselves. The moment marks a turning point, the beginning of a new chapter in our quest for knowledge, challenging our assumptions and inspiring us to expand our horizons. The discovery of this unusual radio signal has sparked intense debates within the scientific community due to its mysterious nature. Some researchers see it as potentially signaling extraterrestrial intelligence, an advanced civilization trying to contact us across the cosmos. They argue that the signal's spectral and polarization features exceed what natural astrophysical processes typically produce, suggesting possible intelligent design or a deliberate transmission. Proponents emphasize exploring all options and maintaining open-mindedness, especially given past surprises like fast radio bursts and pulsar emissions. which initially baffled scientists before natural explanations became clear. They caution against dismissing unexpected signals too quickly, noting that discoveries such as pulsars were once met with disbelief. For them, detecting alien technology warrants increased efforts, more listening stations, international cooperation, and rigorous verification to prevent false claims or sensationalism. Conversely, skeptics argue that extraordinary claims require solid evidence, which is currently lacking. They point out that the signal's brief, non-repeating nature makes it suspicious. Critics suggest it could be caused by unknown natural phenomena, such as energetic cosmic events involving neutron stars, black holes, or plasma processes. Since the universe is a vast and unpredictable laboratory, misattributing signals to extraterrestrial sources without strong proof could overshadow natural astrophysical explanations. Further controversy surrounds the interpretation of the signal's features. Its polarization and spectral traits have led some to speculate about technological origins, like electromagnetic engineering. A minority propose that spacecraft, space debris, or artificial structures could produce similar effects, especially if orbiting or passing through the galaxy. Skeptics, however, argue that without clear markers, such as intentional encoding or repeated signals, these features are probably incidental artifacts or interference, rather than evidence of alien technology. Technical challenges in confirming the signal's nature fuel debate. Some advocate establishing a global network of synchronized radio observatories to verify detection, while others warn against rushing to conclusions. Premature interpretations could lead to misconceptions, either falsely claiming contact or dismissing genuine phenomena due to a lack of reproducibility. Patience and careful analysis are regarded as essential to avoid misinformation. Ethical considerations add another dimension. If the signal is an intentional message, questions arise about our responsibilities in decoding or responding. Active communication might carry risks, possibly exposing humanity to threats from an advanced civilization. Some warn against broadcasting our presence more widely into space, fearing an unanticipated response. Others emphasize international consensus and protocols before any active reply, highlighting cautious diplomacy. The role of government agencies and private organizations in investigating these signals stirs controversy. Critics worry that secrecy or corporate interests could influence interpretations and public disclosures, leading to misinformation or panic. Conversely, many see collaboration among nations as crucial, pooling resources and expertise to understand what could be among mankind's most significant discoveries. Ensuring transparency and collective effort is often viewed as the best approach. Philosophical and societal debates also emerge. Confirming alien communication would challenge humanity's place in the universe, our ideas about life beyond Earth, and the nature of intelligence itself. Some see this as a unifying moment, an awakening to our cosmic context. Others fear societal upheaval, including unrest, fear, conspiracy theories, or religious conflicts that might follow such a revelation. Throughout these discussions, a recurring theme is scientific humility. The universe continues to surprise us, revealing much remains unknown. Many emphasize cautious optimism, analyzing data rigorously, avoiding sensationalism, and remaining open to natural explanations. Recognizing that cosmic phenomena are often more profound than initially understood encourages a balanced approach, curiosity tempered with skepticism. Amid ongoing controversy, one thing is clear: the fleeting signal has already broadened human curiosity and scientific inquiry. Whether natural, extraterrestrial, or something else, it challenges assumptions and pushes frontiers. The world watches as scientists, thinkers, and enthusiasts debate the evidence and ponder this puzzle's significance. The true importance of this discovery depends on interpretation and our response. It requires facing the unknown with skepticism and wonder, honouring curiosity while exercising caution. How we handle this moment could be pivotal, possibly rewriting our understanding of the universe or confirming that we are not alone. The debate persists, each perspective adding to the evolving narrative of our place in the cosmos. Standing at this crossroads, scientists grapple with what the signal might be and what it means for humanity's future. It embodies the tension between scientific rigour and the desire to explore the unknown. As investigations continue, it becomes clear that the discovery raises as many questions as answers, fueling a deeper quest for understanding. The discussion is unlikely to conclude soon, yet its existence encourages us to reconsider our assumptions about life, intelligence, and our cosmic destiny. This ongoing debate highlights both the promise and perils of frontier science. It exemplifies a delicate balance between hope and caution, discovery and skepticism. The signal's nature remains elusive, but its implications are profound, challenging beliefs, inspiring new research, and prompting humanity to reflect on its place in the universe. The outcome could forever alter our cultural, philosophical, and scientific landscape, emphasizing that curiosity must be tempered with wisdom as we explore the greatest mysteries of existence. Since the initial burst was detected, the scientific community has been buzzing with curiosity and activity. Major observatories and research institutions worldwide issued statements emphasizing the find's significance and the urgent need for further investigation. The National Radio Astronomy Observatory in the U.S. acknowledged the anomaly and confirmed follow-up observations with their most sensitive radio telescopes are underway, aiming to detect the phenomenon again or gather more data on its spectral and polarization properties. Similarly, scientists at the European Southern Observatory mobilized optical and infrared telescopes to gather complementary data, checking for transient optical signals or unusual emissions that might correlate with the radio burst. These coordinated efforts highlight the importance of multi-wavelength investigation. Understanding the event likely requires combining radio, optical, and even X-ray observations. Research groups published preliminary reports on preprint servers, describing initial analyses. These reports noted the signal's unprecedented intensity, not only in energy, but in rapid flickering and spectral complexity. Some hints suggested the polarization was extraordinarily high, indicating a unique magnetic environment or process, features that challenge existing models of cosmic phenomena like pulsar emissions, mergers of compact objects, or active galactic nuclei. Institutions like the Harvard-Smithsonian Center for Astrophysics expressed curiosity. Dr. Maria Klein highlighted that such signals challenge current understanding of cosmic plasma physics and emission mechanisms. She indicated rapid variability and spectral features might imply either exotic natural objects or, intriguingly, some form of engineered communication signal, though she urges caution against jumping to conclusions. What has stirred both scientific and public imagination is that several space agencies explore whether the signals could be linked to artificial satellites or human-made interference. Many initial alerts were caused by terrestrial sources such as cosmic rays, satellite radio interference, or ground-based noise. However, rigorous filtering and cross-checks confirmed the burst originated in a galaxy far outside our solar system, making terrestrial interference unlikely. In response, the Breakthrough Listen project dedicated to SETI efforts intensified listening. They directed their most sensitive radio receivers toward the source galaxy, seeking recurring signals or patterns. This is crucial. If the signals are artificial, their repetition or modulation might reveal a message or code. Space agencies like NASA issued internal memos encouraging astronomers and physicists to analyze the event from multiple angles. NASA's Astrobiology Institute stressed understanding whether the signals could stem from unknown natural phenomena, new cosmic objects, or suggest intelligent life beyond Earth. International collaborations formed. Agencies from Japan, China, South Korea, and Australia contributed observational resources. The Australia Telescope Compact Array, in the Outback, reported preliminary data indicating no repeat signals so far, raising questions about the event's fleeting nature and high intensity. Academicians and amateurs scrutinized data, attempting to decode potential patterns. The SETI community issued cautious statements, emphasizing that it's too early to declare extraterrestrial origin. However, this anomaly warrants serious scientific scrutiny. Many recall that history shows many initial signals dismissed as errors or natural phenomena later turned out to be profound discoveries. Meanwhile, some institutions maintain a cautious stance. The European Space Agency's Astrophysical Division issued a statement emphasizing that extraordinary claims require extraordinary evidence. They advocate a thorough, multidisciplinary approach before jumping to conclusions, noting analyzing such signals involves complex math, physics, and philosophical considerations about evidence and interpretation, especially when signals defy current understanding. Growing awareness exists around broader implications. governments and international bodies consider protocols, what actions to take if the signals are confirmed as artificial. The United Nations Office for Outer Space Affairs reportedly convened an emergency session, emphasizing humanity must approach this discovery with curiosity and caution. Despite caution, investigations continue relentlessly. Major observatories dedicate resources and time to study the galaxy, with efforts possibly spanning weeks or months, depending on whether similar signals reappear. Researchers meticulously analyze data for subtle signatures, modulation patterns, frequency shifts, and other hallmarks that might reveal origin, purpose, or technology. An undercurrent of excitement suggests these investigations could solve the puzzle of this specific signal, but also mark a new era in astrophysics. Could this open windows into phenomena never before seen? Might we discover new physics, or detect intelligent extraterrestrial signals? Or are these signals natural cosmic coincidences, rare but explainable events? Whatever the case, the unified response from scientific institutions demonstrates how a single anomaly can spark a global effort blending curiosity, skepticism, and hope. Humanity waits with bated breath, caught in the thrilling uncertainty of the universe's deepest mysteries. The search continues, and perhaps with it, the start of a new dialogue with the cosmos. Despite ongoing investigations, the event has heightened global awareness of the universe's vast unknowns. The hints of possible intelligent signals have sparked debates on scientific, philosophical, and political levels. Many recognize a potential paradigm shift, possibly revealing natural phenomena beyond current models or a new form of intelligence. Still, patience, rigorous analysis, and proof are emphasized before definitive conclusions. Meanwhile, the scientific community remains vigilant, pursuing every lead. High-powered telescopes and sensitive detectors scrutinize the region repeatedly, diligently searching for recurrence or additional clues. Each observation is carefully analyzed, trying to distinguish signal from noise. Researchers consider all possibilities, exotic natural objects or engineered signals, keeping an open mind while adhering to scientific rigor. Public fascination is palpable, fueled by media coverage and social media. This event highlights humanity's desire to find companionship in the cosmos and underscores the importance of scientific caution. Enthusiasm coexists with skepticism as scientists balance excitement with responsibility, understanding that extraordinary claims demand extraordinary evidence. In this pivotal moment, the global scientific effort exemplifies collaboration and humility. The collective endeavor to decipher this signal reflects humanity's resilience and curiosity, driving us to look beyond our surroundings, question our understanding, and prepare for profound discovery. Whatever the outcome, this event reminds us of the universe's complexity and the relentless pursuit of knowledge that defines science. The search for answers continues with renewed vigor as investigations extend over weeks or months, analyzing data and seeking recurring patterns. Researchers explore natural explanations such as unknown cosmic phenomena or previously unseen objects, while also considering artificial origins. The possibility that the signals could herald contact with extraterrestrial intelligence fuels both hope and skepticism. Media coverage amplifies public interest, with social platforms buzzing about the potential for a groundbreaking discovery. This collective curiosity underscores a fundamental aspect of human nature: our desire to connect with the cosmos and our search for meaning beyond Earth. Yet scientific rigor remains paramount. Verifying the signal's origin requires patience, meticulous analysis, and confirmation. Many experts argue that it is premature to draw definitive conclusions, emphasizing the importance of cautious interpretation and the need for extensive follow-up data. Some institutions advocate a multidisciplinary approach, combining physics, astronomy, and philosophical considerations to understand signals that challenge existing models. The event has sparked global discussions on protocols and preparedness. The United Nations Office for Outer Space Affairs reportedly convened an emergency session, highlighting the significance of coordinated international response strategies should the signals prove artificial. Such protocols aim to unify actions, avoid misinterpretations, and prepare humanity for potential contact scenarios. Despite these measures, the scientific community remains open-minded, actively pursuing every lead. Advanced, high-sensitivity telescopes are employed to monitor the source continuously, looking for signs of recurrence, modulation, or patterns indicating artificial intelligence or intentional communication. Each new piece of data could shed light on the signal's nature, purpose, or the technological sophistication behind them. Whether these signals lead to profound discovery or natural explanations, the overall process itself exemplifies human resilience, curiosity, and humility. The event has reawakened global curiosity about the universe, fueling debates about our place in the cosmos and the potential for intelligent life beyond Earth. In the face of uncertainty, scientists, governments, and the public alike demonstrate patience and a commitment to scientific rigor. The event's significance extends beyond the immediate investigation, prompting reflection on humanity's collective pursuit of knowledge and our readiness for possible contact with extraterrestrial intelligence. As investigations continue, the world watches with bated breath, recognizing that each new discovery has the potential to transform our understanding of the universe forever. The anomaly has ignited a global dialogue, scientific, philosophical, and cultural, about what lies beyond our current reach and our preparedness to confront the unknown. Whatever the outcome, this unprecedented event underscores the importance of scientific collaboration, humility, and perseverance. Humanity's quest for understanding drives us to explore the mysterious signals, learning more about the universe and ourselves in the process. The search endures, and with it, the possibility of opening a new chapter in cosmic discovery. As the world's brightest minds mobilized to decipher this cosmic enigma, a mosaic of hypotheses began to emerge. Some experts leaned heavily on the realm of natural phenomena, proposing explanations rooted in exotic astrophysics, while others entertained more speculative ideas, pondering the possibility of intelligent life making its subtle presence known across space. One of the most widely discussed natural explanations centers on highly magnetized neutron stars, known as magnetars. These celestial bodies, characterized by intense magnetic fields, could produce strange radio emissions under certain conditions. Some scientists suggest the signals might be the chaotic aftermath of starquakes, massive fractures in neutron star crusts, that release magnetic energy and produce bursts of radio waves. Others propose magnetic interactions with surrounding plasma might generate complex polarized radio signals that evolve rapidly, mimicking the fleeting detected burst. Yet this theory struggles to fully account for some of the signal's spectral peculiarities. The signals displayed unusual polarization and frequency sweeps that do not neatly fit behaviors observed in typical magnetaire emissions. This discrepancy has sparked debates about whether known astrophysical objects can mimic such signatures, or if we are witnessing a new type of celestial phenomenon altogether. Another hypothesis involves the dynamic environment of black hole accretion disks and their jets. In the turbulent regions around supermassive black holes, magnetic fields are complex and plasma flows turbulent. Some experts speculate interactions here could produce transient radio signals with unusual polarization and spectral properties. These bursts might mark magnetic reconfigurations or shocks within jets, creating signals that briefly pierce space with peculiar features. But this theory also encounters challenges, especially regarding the signal's rapidity and specific spectral features. Such emissions would need to originate from highly localized events or processes not yet fully understood. Researchers continue examining data from black hole systems to see if similar signals have been overlooked or if this burst stands apart in its uniqueness. Beyond natural explanations, hypotheses involving advanced extraterrestrial technology have emerged. A radical idea suggests the signals could be artificial, deliberate messages or beacons sent by an intelligent civilization. The spectral and polarization characteristics might be intentional, crafted to stand out amid cosmic noise and signal the presence of a technologically capable species. Proponents of this idea point to the potential for narrowband signals, highly focused in frequency, that are typical of human communications and might be produced by alien civilizations. They argue the fleeting signals could be quick pings, designed to test detection capabilities or attract attention. The signal's features could be engineered to carry complex information or serve as interstellar lighthouses, signaling to distant observers that another intelligent life form is attempting contact. However, skeptics caution against wild interpretations. The universe is filled with natural phenomena that can mimic artificial signals, and the lack of a clear, repeatable pattern makes it difficult to definitively claim an intelligent origin. This possibility fuels debate, prompting researchers to refine detection techniques in hope of further signals clarifying their nature. Some scientists consider hybrid hypotheses, The signals might arise from natural cosmic processes capable of mimicking artificial phenomena, such as interactions with dark matter or unknown particles. These new views suggest the universe could harbour exotic physics yet to be discovered, phenomena that produce signals with properties resembling those expected from intelligent sources, but are entirely natural. Others emphasise caution, arguing more data is needed before conclusions. They insist extraordinary claims demand extraordinary evidence and seek more precise measurements, broader frequency coverage, and longer observational periods to detect repetitions or patterns. Fringe hypotheses also exist, ideas that stretch beyond conventional thinking. Some speculate these signals could be echoes of ancient cosmic events or remnants of phenomena long past. Others suggest they might be signatures of unknown astrophysical objects, perhaps a new class of sources challenging existing classifications and forcing us to rethink the fundamental physics of our universe. Amid these diverse hypotheses, one thing remains clear: humanity is on the precipice of profound discovery. Whether these signals originate from natural cosmic fireworks, elaborate astrophysical mechanisms, or faint whispers of intelligent civilizations, efforts to understand them could redefine our perception of the universe. Every theory and observation pushes current knowledge, posing new questions, igniting debates, and fueling human curiosity about whether we are truly alone, or if the universe is speaking, waiting for us to listen more carefully. Could this object pose immediate threats to Earth or our solar system? This question arises as scientists and enthusiasts grapple with an extraordinary discovery. Currently, there's no evidence suggesting any imminent danger to our planet. But like many cosmic mysteries, the answer is layered and complex. First, consider the scale and nature of this object. It emits intense, fleeting radio signals from a galaxy millions of light years away, with properties that defy current understanding. The object appears to be located in a remote extragalactic environment, far beyond our solar neighbourhood. Its distance alone provides a natural safeguard. Any potential impact or destructive force it might harbour is virtually impossible to reach Earth soon. Space is vast, and objects billions of miles away do not pose an immediate risk unless on a collision course with us. However, the situation becomes more complex when considering what these signals might represent. Are they natural phenomena, like highly magnetized neutron stars, magnetars, which can unleash powerful electromagnetic bursts? Or could they be signatures of something entirely different, perhaps indicating technologically advanced life? If it's the former, the risk remains minimal. Cosmic objects, even magnetars, generally do not threaten Earth outside rare events like gamma-ray bursts, intense blasts capable of stripping away the atmosphere if directed at us. Still, the likelihood of such a burst from this specific transient one-time event hitting Earth soon is astronomically low. What about the possibility of artificial origin? The thought that we might be witnessing extraterrestrial technology shifts the risk assessment into profound uncertainty. Would an advanced civilization send objects capable of sending signals affecting our solar system? It's purely hypothetical. So far, the signals do not show signs of deliberate aggression or destructive intent. Scientists emphasize analyzing the signal's content. Are they communication attempts, accidental emissions, or indicators of engineering? Moreover, the signal's transient nature and lack of any physical object mean there's no immediate physical threat. No meteoroids, dangerous particles, or radiation levels endangering Earth or spacecraft. Our current observational tools do not detect incoming debris or forces impacting our planet. Although the energy levels on a cosmic scale are immense, they disperse over vast distances, posing no direct threat. Nonetheless, this discovery highlights the universe's unpredictability. Many objects and phenomena could influence our solar system or Earth's environment in the future. For example, comets and asteroids have caused mass extinctions in Earth's distant past, and ongoing surveys aim to find potentially hazardous objects long before they threaten us. Compared to such threats, this cosmic anomaly is more of a puzzle than a danger, prompting inquiry rather than alarm. Scientists worldwide are vigilantly monitoring the region where these signals originate, hoping for more emissions or evidence clarifying its nature. So far, data shows no change in behaviour that could signal an impending event. The fleeting flashes may be natural, high-energy processes that are rare, but not necessarily threatening. In terms of potential threats, if, hypothetically, this object were part of a larger system or target, then the most plausible risk might involve technological interference or contact. But this remains speculative. The signals do not resemble weapons or hostile devices. They could be cosmic beacons or accidental emissions. Their purpose and origin are too uncertain to determine any malicious intent or danger at this stage. The best approach to fears of threats is continued observation and scientific analysis. Monitoring agencies, telescopes, and space organizations are tracking this anomaly carefully to understand it thoroughly. If a threat emerges, early detection would be vital, offering time to prepare or develop countermeasures. Currently, the consensus among astrophysicists is reassuring. There's no immediate danger. While the discovery fuels imaginations about alien invasions or catastrophic events, it's important to base our understanding on current evidence. The universe is vast, and many phenomena are awe-inspiring yet harmless. Our planet remains safely within the heliosphere, protected by space's vacuum and our atmosphere, which shield us from cosmic radiation and particles. This object may not threaten Earth directly, but it has the potential to reshape our understanding of the universe. Its signals are an invitation, a call to examine more carefully, analyze diligently, and stay open to the universe's endless surprises. The mystery continues to unfold, and as it does, our place in the cosmos feels both humbling and profound. In conclusion, while the object is unlikely to pose an immediate threat, it emphasizes the importance of ongoing vigilance and scientific inquiry. It underscores how much remains unknown, and how cautious curiosity must guide us. The universe is a vast, complex place, and phenomena like this remind us of our vulnerability and potential for discovery. As scientists monitor and analyze, the hope is to better understand the signals and ensure Earth's safety. Until then, it remains a cosmic puzzle, one that challenges and inspires us to look deeper, think clearer, and recognize how small we are in the grand universe. Could this mysterious phenomenon open new pathways for interstellar exploration, unlike anything humanity has attempted before? Its very nature invites us to look beyond our current technological horizon and envision a future where interstellar travel depends on understanding, and perhaps harnessing, such cosmic anomalies. Imagine that this fleeting signal, veiled in cryptic spectral and polarization patterns, isn't just a cosmic accident but a beacon, potentially a message or sign of something more deliberate than natural processes. If we consider the provocative idea that it could be a sign of extraterrestrial intelligence, then our exploration scope expands from scientific curiosity to a quest for potential contact. Would humanity see this as a call to act, to reach out or follow the trail left in the dark between stars? Suppose this burst is part of a larger undiscovered communication network, spanning galaxies or civilizations. Deciphering it could propel us into an era where interstellar navigation isn't solely guided by physical laws, but by understanding cosmic signals language. In this scenario, probes wouldn't just listen, but respond, attempting to engage with these messages. Such efforts might lead to technological advances capable of bridging cosmic distances, transforming propulsion, energy concepts, and paving pathways for manned ships or autonomous explorers to reach distant worlds. Unraveling these brief energy bursts could revolutionize physics and engineering. If linked to phenomena like the magnetic fields of neutron stars or magnetars, they might shed light on energy extraction methods far more efficient than current techniques. Harnessing cosmic powerhouses could spark breakthroughs in energy production and propulsion, pushing the limits of what's physically possible. Spacecraft might even ride these energetic waves to travel interstellar distances at speeds once only dreamed. Further investigating this event might spur new detection technologies capable of sensing beyond radio waves to other cosmic emissions. Advancements would enable more comprehensive scans of the universe, revealing hidden structures or signals, possible navigational beacons or shortcuts, guiding our journeys through the galaxy. By refining our observational toolkit, we could discover new phenomena and utilize them as cosmic signposts or pathways. There's a philosophical dimension as well. This discovery compels us to see interstellar exploration as more than science. It's a bold step in our evolution. If intelligent life exists elsewhere and communicates in ways we are just beginning to understand, seeking these signals becomes an extension of our innate curiosity. The search for meaning in these bursts isn't just scientific, it reflects our fundamental drive to explore, connect, and find our place in the cosmos. As understanding deepens, we might develop strategies for shielding explorers from unknown cosmic hazards, or for negotiating with potential extraterrestrial intelligences. Lessons from these bursts could inform design principles for interstellar vessels, helping them survive environments hostile or radically different from Earth. Such insights could be vital in preparing for encounters and ensuring future missions' safety and success. Could this phenomenon mark a new era, where signals, cues, and knowledge from the universe itself guide interstellar travel? It's plausible. These signals could act as cosmic signposts, leading explorers to promising star systems, ancient civilizations, or even fundamental aspects of reality. Every discovery might bring us closer to mastering faster-than-light travel or teleportation, transforming interstellar exploration from a dream into reality. In summary, this cosmic event isn't just a scientific curiosity. It's a catalyst for profound change. It challenges our notions of what's possible and urges us to innovate boldly and think creatively. Whether natural or intelligent in origin, these mysteries beckon us to venture further, reach deeper, and find a way across the stars. They push the boundaries of human achievement, inspiring new technologies and ideas, expanding our universe. This phenomenon could fundamentally alter our approach to exploring beyond our galaxy. It pushes the limits of imagination and technology, hinting that the future of interstellar travel depends on deciphering signals or harnessing energetic phenomena we're only beginning to understand. Such signals might be guides, keys, or pathways, leading us to distant worlds, ancient civilizations, or the fabric of reality itself. Every step in understanding these cosmic mysteries advances humanity into a new frontier. The potential for signals to reveal shortcuts, hidden paths, or new physics means the search isn't just about understanding the universe, it's about expanding our own boundaries. Whether these phenomena are natural or signs of intelligent life, they call us to venture further, to reach deeper into the cosmos. These mysteries offer the possibility that interstellar exploration might soon be guided by signals from the universe, shaping future missions and breakthroughs. They could help develop technology capable of navigating or communicating across cosmic scales. Humanity's curiosity and drive to explore are reignited by the prospect of deciphering these messages, leading to a future where we cross the stars. Ultimately, this fleeting cosmic event isn't just an anomaly, but a doorway to extraordinary advancements. It challenges us to think bigger, to dream beyond current limits, and to prepare for a future where understanding cosmic signals drives interstellar travel. These mysteries call us to push onward, venture further, and maybe find a way to bridge the vast distances between stars. As scientists and observatories worldwide scrutinize this enigmatic cosmic anomaly, one question looms: what if this object displays unexpected behavior? In cutting-edge astrophysics, confronting the unknown requires preparing for the unpredictable. Protocols are swiftly enacted, not only to protect valuable equipment, but also to safeguard the integrity of the investigation and manage any emerging threats, physical, technological, or existential, with caution. The international scientific community has established a framework of immediate actions to activate if the object exhibits behaviors deviating from initial observations. Such behaviors might include increased emission intensity, altered spectral or polarization properties, shifts in frequency, or new signals that challenge current understanding. These deviations could indicate natural yet dangerous astrophysical processes, or, more speculative, the manifestation of artificial or intelligent origins responding in unforeseen ways. In these cases, rapid communication through established channels, an emergency alert network, is essential. Leading observatories, space agencies, and research institutions are equipped to disseminate real-time data immediately. This includes notifying astronomers, astrophysicists, planetary defense agencies, and governmental bodies. The aim is to enable a coordinated response, utilizing the global network of telescopes and detectors to gather as much information as possible and assess the change's nature and scope. Safety protocols also prioritize safeguarding personnel and expensive equipment. Ground-based observatories may have automated shutdown mechanisms or emergency procedures to be enacted swiftly if dangerous radiation levels are detected or if the behavior suggests high energy instability. For example, if the emission intensifies exponentially or exhibits erratic signals, observations might be temporarily suspended to protect sensitive instruments from overload or damage. In space-based facilities, autonomous systems are programmed with protective objectives. These include adjusting diagnostic instruments, deploying shielding, or retreating from the source if a threat level is high. If the object emits high-energy particles or gamma rays unexpectedly, spacecraft may go into safe mode, minimize activity, or orient shields toward the source to buffer impact. Addressing the possibility of an artificial or intelligent origin, many organizations have safety measures for potential technological artifacts or signals of non-human origin. These include firing alert protocols that restrict or turn off sensitive data sharing. Preventing interception or misuse might lead to misunderstandings. The emphasis is on cautious engagement, establishing secure, monitored communication channels that avoid misinterpretation or escalation. Scientists also recognize the societal and psychological impacts of sudden anomalies, especially those indicating extraterrestrial intelligence. To prevent misinformation and panic, official communication channels and public information protocols are carefully managed. Teams of crisis communication specialists, scientists, and policymakers prepare to deliver clear, transparent messages, avoiding sensationalism or misinterpretation. Their goal is to inform the public with accurate data while minimizing unnecessary alarm. Broader contingency plans involve an ethics and safety review board dedicated to monitoring developments related to this object. This board evaluates whether to escalate or de-escalate observation efforts based on behavior, ensuring responses are measured, justified, and ethically sound. If behaviors suggest hazardous phenomena such as energy explosions, space-time deformation, or electromagnetic interference, officials can recommend halting certain activities, adopting cautious observation techniques, or initiating international dialogue on responses. In extreme hypothetical scenarios, where the object produces signals or behaviors threatening Earth's technological infrastructure, additional protocols activate. These could include securing critical communications, deploying backup systems, or temporarily suspending sensitive operations. Such measures aim to contain any technological fallout and prevent widespread chaos. The overarching principle of all safety protocols is humility paired with prudence. Scientists understand they're exploring uncharted territory where surprises are possible. Safety measures focus on preparedness, recognizing that understanding the universe's mysteries involves humility, vigilance, and agility. The measures are less about control and more about readiness for all eventualities. As the situation develops, continuous monitoring remains crucial. Data streams feed into artificial intelligence algorithms designed to detect anomalies automatically and recommend responses in real time. These systems implement layered safety approaches. Initial responses involve increased observation and data collection, escalating to protective shutdowns or alerts if thresholds are crossed. Throughout, the core goals are clear: ensure scientific discovery proceeds responsibly, protect facilities and personnel, and prepare for any eventuality, whether a natural cosmic event, technological anomaly, or something beyond human understanding. It's a delicate balance, an interplay between curiosity and caution, as humans extend their reach into the cosmic ocean, seeking answers while guarding against the unforeseen. Absolutely, the potential for this discovery to revolutionize technology is profound and far-reaching. When science uncovers the universe's deepest mysteries, history shows that groundbreaking breakthroughs often follow, leading to innovations that transform daily life. For example, quantum mechanics, initially theoretical, became crucial for modern tech like smartphones, encryption, and quantum computing. Could this space phenomenon serve as the next catalyst for revolutionary advances? The answer is yes. Understanding these signals could unlock new scientific and technological horizons. Researchers worldwide are investing heavily in probing these intense, fleeting signals with unique spectral signatures and polarization properties. These challenge current physics, suggesting origins in environments beyond known extremes, such as neutron star magnetospheres, black hole accretion disks, or possibly artificial sources from advanced civilizations. As scientists delve deeper, this research could reveal fundamental insights into matter, energy, and space-time, often leading to unforeseen applications. For instance, studying black hole environments has historically spurred advances in plasma physics, materials science, and high-power laser tech. One promising avenue involves creating new materials and energy systems. If these signals stem from exotic interactions, like intense magnetic fields or shock waves, understanding their sources could inspire resilient magnetic materials that withstand extreme conditions. Such materials have potential in power grids, fusion reactors, and aerospace engineering. Moreover, the physics behind these bursts might inspire novel energy harvesting, transmission or storage methods, making our energy infrastructure more efficient and sustainable. Technologically, detection and analysis techniques for these signals are themselves drivers of innovation. Currently, radio telescopes, high-speed data processing, machine learning classifiers, and noise filtering are crucial to identify these phenomena. Advances here could translate to terrestrial applications, secure communications, remote sensing, or high-speed data centers with error correction. Quantum encryption techniques, relying on quantum properties, could be enhanced through polarization and spectral coding methods inspired by astrophysical signals, leading to near-unbreakable communication. Another key development involves ultra-sensitive sensors capable of processing enormous data streams in real time. Progress in sensor tech, signal processing, and AI-driven analysis could benefit fields beyond astrophysics. Medical imaging, such as MRI resolution improvement, seismic detection of early earthquake precursors, environmental monitoring of pollutants, and defense systems could leverage these innovations. High-sensitivity sensors capable of detecting faint signals amid noise open avenues for breakthroughs in various high-demand domains. Furthermore, if investigations reveal these signals originate from artificial sources, it would radically transform our technological landscape. Humanity would need to develop protocols for interstellar messaging and communication systems. Transmitting and decoding cosmic messages could accelerate advancements in AI, machine learning, and cryptography, essential for interpreting complex encoded signals. Such progress could lead to ultra-advanced communication networks capable of bridging interstellar distances, resilient, scalable, and secure. Deciphering extraterrestrial communications would revolutionize our understanding of linguistics, mathematics, and cryptography, with implications for cybersecurity and data encoding. It could catalyze a new wave of technological innovation in how we share information internally and across borders, fostering a more connected, secure global society. Beyond communication, insights from these signals might drive advances in fundamental physics. Each detail may reveal previously unknown principles, potentially aiding efforts to unify quantum mechanics and general relativity. Historically, breakthroughs in foundational physics have spurred technological revolutions. GPS relies on relativity, while quantum theory underpins electronics. Understanding cosmic phenomena could inspire new propulsion, energy, and materials innovations, transforming how we harness power and explore space. On a broader level, exploration of these signals embodies human curiosity's aspirational spirit. It could ignite global interest in science, motivate educational initiatives, and inspire future scientists and explorers. The quest to understand the cosmos unites humanity in a common pursuit, fostering collaboration, innovation, and wonder about our place in the universe. In sum, investigating these space signals isn't merely academic, it's an opportunity for revolutions across multiple sectors. Every discovery, new method, or material contributes to societal progress. The innovations could reshape energy, communication, materials science, computing, and physics. Historically, understanding the cosmos has led to technological leaps. Given their mysterious nature, the potential for breakthroughs is immense. Once understood, they could usher in a new era of human development. Decoding these messages might become the next major leap in our technological evolution, driven by curiosity, ingenuity, and the human desire to explore the unknown. Exact words 692. Scientists around the globe are actively mobilizing tools and strategies to investigate this mysterious cosmic signal. Powerful telescopes, both on Earth and in space, are being directed towards the source to gather more data, details, and clarity. This effort isn't limited to any single observatory or country. It's a worldwide initiative driven by collective curiosity that crosses borders. Leading the effort are radio telescopes like the Very Large Array in New Mexico, which are focusing their enormous dishes on the source. Multiple dishes working together allow astronomers to pinpoint the burst's location with astonishing accuracy, enabling targeted follow-up observations. Space telescopes such as the James Webb Space Telescope and Chandra X-ray Observatory are also being employed. These instruments observe in different wavelengths, infrared, X-ray, ultraviolet, adding layers of information that radio waves alone cannot provide. Capturing emissions across the spectrum may reveal whether the burst is associated with energetic events, such as black holes, neutron star collisions, or entirely new phenomena. Astronomers are also using rapid response follow-up techniques. When such a burst is detected, alerts are issued almost instantaneously across international observatories, triggering a flurry of activity. Optical telescopes, gamma-ray detectors, and neutrino observatories respond immediately, seeking coincident signals that might shed light on the event. Wide-field surveys monitoring large portions of the sky play a crucial role. Projects like the Vera-C Rubin Observatory, with its 8.4-meter mirror and all-sky imaging capability, are key. They could detect similar transient events in real time, building a statistical library to identify patterns or recurring features of these bursts. Some scientists are contemplating more speculative methods, such as deploying small autonomous space probes closer to the source, if technologically feasible, to gather in situ data. While sounding like science fiction now, technological advances could make deploying small spacecraft for detailed follow-up a future reality. Alongside observational efforts, theoretical and computational modelling are intensifying. Researchers are developing sophisticated simulations to understand potential natural sources of these signals, extreme magnetic activity, novel stellar explosions, or new phases in galaxy evolution. Advanced data analysis, including machine learning algorithms, are being used to sift through vast data volumes, searching for subtle clues or correlations that might escape humans. Collaborative efforts are forming unprecedentedly, uniting astronomers, physicists, computer scientists, and engineers. The goal is to create a global data sharing network that enables rapid cross-referencing, sparks new insights, and prevents potential leads from being overlooked. Such cooperation is vital given the transient, fleeting nature of these signals. Several projects are considering dedicated new instruments optimized for transient detection. For example, next-generation radio arrays with enhanced sensitivity and faster response times are under development. These could detect signals that are even more fleeting or weak, broadening the scope of discovery. International conferences and workshops focused on this anomaly are becoming hubs for sharing findings, brainstorming hypotheses, and coordinating responses. Funding agencies worldwide recognize the importance of this research and have increased support, knowing solving this mystery could redefine astrophysics. All these efforts share a fundamental understanding that this isn't just about understanding an isolated event, but about opening a new chapter in understanding the universe itself. Each observation, data point, and theoretical insight moves scientists closer to uncovering phenomena that challenge current physics, possibly leading to revolutionary discoveries. Time is a critical element. These bursts are fleeting, lasting milliseconds to seconds. Every second counts, and scientists are racing against this clock to observe and decode as many signals as possible. The pace is rapid, stakes high, and potential rewards enormous. If the source is something genuinely unknown, beyond current natural explanations, it could spark a scientific revolution comparable to the discovery of the cosmic microwave background radiation decades ago. In the coming months and years, with ongoing effort and curiosity, scientists hope to peel back the veil on this cosmic mystery. Whether it turns out to be a natural phenomenon pushing astrophysics boundaries, an artificial signal from extraterrestrials, or something entirely unforeseen, one thing is clear: scientists are more motivated than ever to unravel this puzzle. They aim to unlock secrets of the universe that these signals might conceal, pushing the frontiers of human knowledge. As the investigation into this cosmic conundrum heats up, it's incredible to see the array of observatories and space missions now aiming their tools at the universe, each playing a vital role in unraveling the mystery. These scientific eyes, from ground-based telescopes to space observatories, form a global and interstellar network dedicated to peeling back the layers of this enigma. Beginning with radio astronomy's backbone, the Very Large Array in New Mexico is a key player. Its 30 interconnected dishes spread across a vast desert detect fast radio bursts, especially sudden, intense signals like the one igniting this investigation. Its ability to pinpoint exact locations guides astronomers to the host galaxy and helps understand the environments where these phenomena occur. Equally important is the Canadian Hydrogen Intensity Mapping Experiment, CHIME, in British Columbia. CHIME employs a cylindrical array capable of monitoring large sky sections simultaneously. When the burst occurred, CHIME was among the first to detect it, providing crucial real-time data that raised worldwide interest. Its continuous sky surveillance is transforming our capacity to study these elusive signals, turning transient cosmic events into detailed data sources. Beyond terrestrial observatories, space telescopes bring unique viewpoints. NASA's Neil Armstrong Space Telescope, with high-resolution X-ray and ultraviolet instruments, is on standby, ready to analyze the burst's high-energy counterparts. Its recent upgrades enable it to assist in multi-wavelength observations, offering insights into potential origins like neutron stars or black hole accretion disks. The European Space Agency's X-ray multi-mirror mission, XMM Newton, adds another perspective by observing high-energy photons. Its sensitivity could reveal if the signal relates to extreme processes, such as collapsing stars or emissions from magnetars, neutron stars with intense magnetic fields. Its quick repositioning makes it vital for transient event investigations. The James Webb Space Telescope, the most anticipated modern observatory, provides invaluable infrared data. Though primarily designed for looking back in time at early galaxies, JWST's instruments can examine the burst's host galaxy, analysing its composition and star formation activity. Comparing the host with others helps scientists understand if extraordinary environments generate such mysterious signals. Meanwhile, the Atacama Large Millimeter-Submillimeter Array, ALMA in Chile, observes in millimeter wavelengths. ALMA can detect cold, dense regions of space, star-forming areas, or molecules around the burst source, shedding light on the physical conditions involved. These observations help determine if the event originated in regions rich in specific molecules, pointing to processes like star formation or black hole activity. Within the near future, the Chinese space station telescope aims to deploy advanced multi-wavelength instruments to contribute further data. Upcoming projects like the Square Kilometre Array, SKA, set to be the world's largest radio telescope array spanning South Africa and Australia, promise a revolution in radio astronomy. Once operational, it will detect faint or distant bursts with unprecedented sensitivity, providing vital context for current mysteries. All these observatories work in concert, sharing data streams, coordinating rapid reactions to burst detections. This multi-wavelength, multi-messenger approach, combining radio, optical, infrared, X-ray and gamma-ray observations, aims to create a comprehensive picture of the event's origins, environment and implications. The synergy of ground and space-based platforms forms a powerful network that accelerates our understanding, shaping future theories. Adding to this effort are transient alert systems like the Gamma Ray Coordinates Network, which relay real-time data about fleeting events. These systems enable telescopes worldwide to swiftly pivot and observe the same target from multiple angles. Such rapid, coordinated responses are crucial to capturing the event before it fades, often within milliseconds to seconds. Looking ahead, collaboration extends further. Data archives from missions like Hubble or Chandra are being examined for historic signals or environmental clues relevant to this event. The hope is that patterns could emerge, indicating recurring phenomena or subtle hints that might lead to a definitive explanation. This global, interstellar team of observatories embodies the spirit of modern astrophysics, collaborative, multidisciplinary, and relentless in pursuit of answers. Every spectrum, image, and data point brings us closer to understanding whether this mysterious signal is a natural cosmic accident, a whisper from alien civilization, or a new physics phenomenon waiting to be uncovered. The universe has presented a compelling puzzle, and with this impressive array of synchronized instruments, humanity is actively seeking its deepest truths. The collective effort of these observatories, ground and space-based, demonstrates our resolve to decipher the universe's secrets, advancing knowledge and opening new frontiers of understanding, one discovery at a time. The challenge begins at the core of the analysis. Fleeting signals are notoriously difficult to catch and study. When dealing with radio bursts lasting only a few milliseconds, sometimes less, the window for gathering meaningful data is extremely narrow. Researchers rely on large, highly sensitive radio telescopes spread worldwide. Even then, capturing these events requires luck and precise coordination. Instruments must be aimed exactly at the right spot at the right moment, akin to hitting a tiny moving target in a storm. Often, by the time scientists are alerted, the burst is over or too faint for detailed investigation. timing is critical. Since these bursts are sporadic and unpredictable, continuous monitoring of the sky is necessary. This creates significant logistical challenges. Vast amounts of data are generated constantly, reaching terabytes or petabytes. Storing, processing, and analyzing such data push current technological limits. Extracting meaningful signals from noise or distinguishing genuine bursts from terrestrial interference or instrumental glitches complicates matters further. The universe is filled with human-made signals, satellites, radar, communication beacons that can mimic or obscure cosmic signals scientists seek to understand. Adding to these technical hurdles is the variability of the bursts. Some appear as single, one-off events, others occur in rapid sequences with complex evolving spectral patterns. Untangling this variability requires sophisticated algorithms, often powered by artificial intelligence, to identify patterns and sources. Even with advanced software, interpretation remains challenging. Variations in frequency, polarization, intensity, and duration demand a multifaceted approach, cross-referencing observations from different instruments and times to assemble a coherent picture. Localization presents another challenge. Pinpointing the exact origin of these signals in vast space is like trying to hear a whisper across an open, noisy field. Most radio telescopes lack sufficient resolution to precisely identify the source without additional multi-wavelength observations. This difficulty hampers efforts to determine if bursts originate from known galaxies, star systems, or unknown celestial objects. Without exact location data, hypotheses about the source remain speculative. Further complicating analysis are the mysterious spectral and polarization features of these signals. Standard astrophysical models struggle to explain such behavior. Researchers often question and potentially rethink theories about how energy is emitted and transferred in space. These spectral signatures don't match known phenomena like pulsars, black holes, or supernova remnants. They seem to defy classification, risking dead ends or incomplete understanding if misinterpreted. Distinguishing a new natural process from artificial signals, possibly from an intelligent civilization, is a nerve-wracking dilemma. The stakes are high, and rushing conclusions can be dangerous, especially without sufficient evidence. Interdisciplinarity complicates matters further. Investigating these signals involves astrophysicists, engineers, data scientists, and even philosophers pondering extraterrestrial intelligence. Coordination across disciplines isn't seamless. Differing techniques, terminologies, and perspectives demand time, trust, and effective communication, which can be difficult under the urgency and curiosity to decode signals before they fade again. Uncertainty about underlying physics poses additional challenges. When data defies all known models, scientists confront questions requiring new physics. What if these signals come from phenomena beyond current understanding of space, time, or electromagnetism? Such possibilities are exciting but intimidating, implying the universe may hide secrets more profound than previously thought. Pursuing this requires pushing computational limits, developing new theories, and remaining open to paradigm shifts, all amid limited observational opportunities which add pressure. Verification and validation are also daunting. A single detection, no matter how promising, needs confirmation. Multiple independent observations across observatories, wavelengths, and signal types are essential. Coordinating these efforts is complex. Weather, technical problems, and resource competition interfere. Yet, without repeated observations and corroboration, claims about the signal's nature remain tentative and uncertain. Collectively, these challenges highlight how much remains before scientists can confidently decode this cosmic message. Each step uncovers new questions, pushes technology to its limits, and demands unprecedented collaboration. Overcoming each obstacle could significantly advance understanding of the universe's secrets, many still hidden. The pursuit is both thrilling and arduous, with every breakthrough promising a leap towards comprehending a universe still full of mysteries waiting to be unveiled. As we stand on the brink of a technological revolution in astronomy, upcoming tools and innovations could deepen our understanding of this mysterious cosmic signal significantly. Future advancements will shatter the limits of current observation, revealing hidden details and secrets long beyond our reach. Advances in radio telescope arrays promise unparalleled sensitivity and resolution. Instruments like the Square Kilometre Array will surpass existing telescopes such as the Very Large Array and the Australian Square Kilometre Array Pathfinder, with a collecting area spanning many square kilometres. These will detect faint signals with extraordinary clarity, enabling us to scrutinize fleeting phenomena such as recent bursts in exquisite detail. This allows dissection of the radio wave's structure, analysis of subtle polarization changes, and the potential identification of patterns or signatures that could indicate artificial origins. Complementing these large arrays are high-speed, real-time data processing systems powered by artificial intelligence. Handling vast torrents of data from these telescopes is challenging. Future AI algorithms will learn to recognize anomalies more efficiently, sift through data at blinding speeds, and identify similar bursts currently missed. They may classify different signal types, and even predict when and where the next event might occur. Machine learning will accelerate the detection of repeatability or unique characteristics, narrowing the scope of potential explanations early in the analysis. Another breakthrough involves space-based observatories with advanced instrumentation. While ground telescopes are limited by Earth's atmosphere, space-based arrays can operate across a broader electromagnetic spectrum, including frequencies absorbed or distorted by the atmosphere. Imagine a constellation of satellites monitoring the sky continuously, detecting radio bursts in real time from their source galaxy, and pinpointing their origin with precision. Such capabilities could determine whether the signal emanates from a specific region within a galaxy, a localized object, like an orbiting satellite, or something entirely unexpected. Infrared, optical, and X-ray observatories will also contribute crucial insights. Future telescopes like the James Webb Space Telescope, equipped with ultra-sensitive instruments, might detect electromagnetic counterparts to radio bursts. Did the event produce simultaneous emissions at other wavelengths? Linking radio signals with optical flares or X-ray outbursts could provide vital clues about the physical processes involved. Observing multiple wavelengths simultaneously and at high resolution helps distinguish natural astrophysical phenomena, like neutron star collisions or black hole activity, from potential artificial signals. Moreover, quantum sensing technologies offer promising new capabilities. Emerging quantum sensors could detect minute variations in magnetic and electric fields around distant objects, revealing details about their environments. This could help determine whether the source results from natural astrophysical processes or something more exotic, possibly artificial. These sensors could also improve the precision of measurements such as timing and polarization, offering insights into the fundamental physics involved in the signals. Fast, sensitive computational models are critical as well. Supercomputers using advanced simulations can model complex cosmic environments, helping scientists compare conditions that produce known signals with new anomalies. Such models might reveal whether unconventional physics, like interactions with dark matter or unknown particles, is necessary to explain these phenomena, prompting us to rethink existing theories. Global collaborative networks will further amplify these capabilities. As new observatories and instruments come online, real-time data sharing between institutions worldwide will become standard. Imagine coordinated efforts where a burst detected by a radio telescope immediately triggers follow-up observations across the spectrum, with AI algorithms analyzing incoming data instantly. Rapid responses could capture subtle clues often lost in transient events, making sure no detail is missed and exploring all angles within hours or even minutes. Finally, next-generation gravitational wave detectors could add profound insights. If the signals connect to cataclysmic events like neutron star mergers or black hole formations, gravitational waves could reveal crucial details. Detecting correlated signals across multiple messengers, radio waves, light and gravitational waves, would provide a comprehensive picture, indicating whether the burst links to known phenomena or something entirely novel. In summary, the convergence of more sensitive telescopes, AI-driven analysis, space-based observatories, quantum sensors, enhanced simulations, and global data networks will drastically improve our ability to investigate cosmic mysteries. We are approaching an era where previously inconceivable observations become possible, where the universe's faint whispers can be amplified into comprehensible stories. These tools will help decode the strange signals, revealing secrets not only about distant galaxies, but about the fundamental laws that govern our universe. Ultimately, the ongoing technological revolution will elevate our understanding, and perhaps, finally, unlock the true nature of these cosmic messages. The discovery challenges everything we knew about our place in the cosmos. It's as if the universe has whispered a secret so profound that it stirs awe, curiosity, and unsettling questions about our role amid the celestial tapestry. For centuries, humankind looked outward with wonder, believing we were alone in a vast, silent universe. Now, with this revelation, be it an ancient signal, anomaly, or natural phenomenon, those assumptions are shaking at their core. Imagine the sheer scale of the universe. Billions of galaxies, each containing billions of stars and planets orbiting countless suns. It's staggering to realize we're just a tiny speck in this infinite expanse. But what if this discovery hints at something more? Could it be a sign we are not alone, that we are part of a larger interconnected cosmic ecosystem? Or could it be something entirely different, so rare or peculiar that it makes us reconsider the universe's underlying physics? The implications extend beyond science. Humanity has long navigated a world defined by immediate surroundings, gradually expanding into space with rockets and telescopes. The discovery of an unusual extraterrestrial signal or natural anomaly raises questions about consciousness, intelligence, and the fabric of reality itself. If signals are from artificial sources, perhaps advanced civilizations beyond our understanding, our place in the universe gains new significance. We wouldn't be isolated beings in a silent void, but part of a larger, bustling community of intelligences. This realization holds profound philosophical and existential repercussions. It challenges the notion that we are the universe's pinnacle or its only life form. Instead, it suggests we are in a cosmic neighborhood filled with unknown, possibly more advanced entities. The implications for our culture, history, and spiritual outlooks are enormous. How does knowing we might share the universe, or be watched or contacted, change our self-view? Do we proceed with humility, awe, or a sense of responsibility? There's also a humbling aspect. The universe is about 14 billion years old and vast beyond imagining. In this grand scale, our species is young, our civilization's only just beginning to understand the cosmos. The discovery underscores how much more we have to learn. It reminds us that what we see and interpret is only a glimpse of a universe far more complex than current theories suggest. At the same time, the revelation fuels curiosity and imagination. It sparks a primal sense of adventure ingrained in human consciousness. Stories of alien encounters, ancient astronomers gazing at the stars, and explorers venturing into the unknown have always been part of human history. Now, it seems we are closer than ever to discovering whether those stories hold truth and whether others gaze back with curiosity of their own. The discovery prompts reflection on our civilization's progress. If we've uncovered an extraterrestrial signal or cosmic anomaly, we've crossed a technological and scientific threshold. We've developed instruments capable of listening across light years, deciphering signals that might be messages, natural phenomena, or warnings. This shows how far we've come, from primitive telescopes to sophisticated arrays and space observatories, able to detect signs beyond our previous understanding. But with new knowledge comes responsibility. If we've found evidence of intelligent life, ethical questions arise. Should we try to communicate, or is it better to listen and learn first, avoiding harm or misinterpretation? Could contact lead to transformative change for humanity, or pose risks we're unprepared for? This discovery mirrors the universe and our society, raising questions about how prepared we are for contact, how we interpret signals, and how we define our role as explorers. It energizes the scientific community, uniting nations and disciplines toward understanding phenomena that challenge assumptions and push knowledge boundaries. The fact that we ponder these enigmas speaks to human resilience and insatiable curiosity. It signifies an evolutionary leap, not only in our technology but also in our collective consciousness. We are becoming a species that actively seeks to understand its place in the universe, rather than passively existing within it. This moment acts as a wake-up call from the universe. It reminds us that the cosmos is an open book, filled with mysteries awaiting interpretation. It urges us to look beyond the horizon, to question, dream, and prepare for what lies ahead. Whether this marks the dawn of first contact or a natural cosmic phenomenon, one thing is certain: humanity's journey into space is only beginning. As we stand on the brink of unraveling this cosmic puzzle, we must remember that our place in the universe is not fixed but a dynamic, evolving story, written one discovery at a time. What lies ahead could redefine us not just as a species, but as explorers of the infinite, endlessly seeking our place among the stars. The discovery of this strange cosmic phenomenon, profoundly challenges our deepest philosophical and religious assumptions. For centuries, humanity has looked at the night sky, wondering if we are alone or if others are out there, perhaps watching or waiting. When the universe reveals something so bizarre that it defies natural explanations, it confronts us with questions beyond science, striking at our beliefs about our place in the cosmos. Philosophically, the implications are staggering. Many philosophies see the universe and life as part of a divine or cosmic plan, a grand design that humans are an integral part of. The discovery of signals or phenomena hinting at artificial origins, possibly extraterrestrial intelligence, could shake these beliefs. If signals from intelligent beings exist, the idea that humanity is unique or that our civilization is the pinnacle becomes harder to sustain. This kind of discovery challenges deterministic views that the universe is a clockwork governed solely by natural laws, by suggesting purpose, intention, or design beyond current scientific understanding. It raises questions about the meaning behind these signals. Are they messages meant to communicate? Are they attempts at contact? Or are they accidental remnants of long-gone civilizations? Each possibility compels us to re-evaluate assumptions about the universe's true nature and our role within it. Religious doctrines also face upheaval. Many faiths hold that humans are special, the divine image bearers, set apart by divine purpose. If intelligent life exists elsewhere or signals from other civilizations are found, questions arise about divine exclusivity. Does divine creation encompass many worlds? Or does this suggest humans are not the only recipients of divine attention? Some might see such findings as challenging the idea that Earth and humanity hold a unique place in divine plans. For certain religious followers, intelligent life elsewhere might seem either blasphemous or a cosmic divine revelation. This raises issues about divine omnipotence and omnipresence. If other beings exist who can send signals, does that imply God's creation is more expansive? Does divine purpose stretch beyond human understanding? Or could this disrupt traditional narratives, requiring theological reinterpretation to reconcile new cosmic evidence with age-old scriptures? Some religious communities might embrace the discovery, viewing it as evidence of a vast, interconnected divine creation, a universe woven with countless civilizations. Others might see it as a test of faith or challenge to traditional teachings, prompting reinterpretations of sacred texts or doctrines. This tension sparks profound introspection, debates about divine omnipotence, human sovereignty, and the ultimate purpose of life. Beyond doctrinal debate, this discovery evokes existential fears and hopes. It prompts crucial questions. If we are not alone, what does this say about our significance? Could other civilizations be more advanced, technologically or spiritually? Are we destined to join a larger cosmic community, or are we to remain isolated, the only life capable of contemplating its existence? The idea that these signals are artificial hints at a universe teeming with advanced civilizations, some potentially millions of years ahead, puts our progress into perspective. It urges reflection on whether we will ever achieve interstellar communication or stay confined to our corner of the cosmos. It forces us to reconsider notions of progress, the purpose of scientific exploration, and whether human civilization is following a unique trajectory or part of an ongoing cosmic saga. As we grapple with these questions, we realize science alone cannot provide every answer. The discovery challenges us to engage with our philosophical, spiritual, and ethical beliefs, pushing us to rethink and expand them. It can inspire awe and humility, reminding us how much more complex and mysterious the universe truly is. Ultimately, these signals are not just a scientific puzzle, they mirror our deepest hopes, fears, and beliefs. They compel us to reconsider what it means to be human, to belong to a universe that might be more diverse, interconnected, and vibrant than we imagined. Whether this discovery unites or divides us depends on our interpretation of the universe's message, a message that could transform everything we thought we knew about ourselves and the cosmos. The discovery of this unusual space phenomenon is already causing ripples through the scientific community, prompting a re-evaluation of space exploration policies. Governments and international agencies are reconsidering their frameworks to address the profound implications of these findings. At the core is a shift in our perception of space. No longer just a frontier for curiosity and technology, space now raises existential questions about humanity's place in the universe. Policymakers recognise that understanding these signals is not only scientific, but intertwined with security, diplomacy, ethics, and our long-term survival. Future policies may emphasise international cooperation, as no single nation can act alone around potential extraterrestrial intelligence or signals. Multinational agreements could facilitate data sharing, transparency, and equitable access, preventing space militarization or unilateral control over discoveries that belong to all humanity. Resource allocation is likely to shift. Governments may increase funding for advanced observatories and space-based detectors to maintain leadership during this breakthrough era, accelerating discoveries and technological progress. Policies might promote global infrastructure for rapid response to transient signals, addressing timing challenges in analysing fleeting cosmic phenomena. Safety protocols could be overhauled, especially if some signals suggest artificial origins. International protocols might be developed for encountering extraterrestrial technology or signals, with global task forces for analysis and response. Guidelines for safe communication, verification, and contingency plans could be established to prevent panic, misinformation, or escalation. Ethics will become central to space policies. Discoveries pointing to extraterrestrial intelligence provoke questions about our responsibilities. Should we reach out or remain silent? How do we avoid damaging potential extraterrestrial ecosystems? Existing treaties and norms may be revised to emphasize ethical standards that respect cosmic sovereignty, an unprecedented move challenging centuries of human-centered policies. Private companies' roles could evolve. Regulations might require private missions to adhere to detection and response protocols, including mandatory reporting of unusual signals, shared infrastructure, and ethical exploration limits. Governments may see private entities as partners rather than competitors in understanding cosmic clues. The discovery might also influence planetary protection policies. If signals indicate alien life or artifacts, agencies may need to review sterilization procedures for spacecraft and celestial bodies, balancing scientific inquiry with the preservation of extraterrestrial environments. Policies would aim to prevent contamination while exploring new worlds. On a broader scope, space policies may become more adaptable and iterative, reflecting the unpredictable nature of discoveries. Task forces or agencies dedicated to analysing signals could operate swiftly, with international organisations facilitating cooperation, security, and intelligence sharing, ensuring a unified response when encountering such phenomena. These breakthroughs are transforming our view of space exploration, shifting focus from expansion to understanding the profound implications of discoveries. Policies are expected to evolve in tandem with questions that intersect curiosity, diplomacy, ethics, and security. Humanity is prompted to develop new guidelines for navigating the final frontier, rules acknowledging our expanding cosmic perspective and responsibilities. This evolution might promote increased collaboration among nations and private firms, sharing mechanisms to detect, analyze, and respond to alien signals. New protocols could prioritize transparency, ethical exploration, and contamination prevention, fostering a global approach to this unprecedented challenge. International standards could be established to facilitate cooperation, ensuring discoveries benefit all humanity. Furthermore, exploration of new celestial bodies might be conducted under stricter guidelines, aiming to protect extraterrestrial environments while advancing scientific understanding. Revisions in sterilization and decontamination procedures would aim to prevent biological or technological contamination. The scientific community may also develop specialized agencies or task forces to coordinate efforts, analyze data, and advise governments. Such bodies would help address the complexities and uncertainties inherent in potential encounters, ensuring responses are based on science and consensus. International cooperation could extend to intelligence sharing, joint missions, and transparent data exchange. Collective efforts would be essential, especially if signals suggest technological or biological threats, to prevent miscalculations and foster trust among nations, reducing conflict over cosmic discoveries. The technological advancements driven by this research, such as more sensitive detectors and rapid data analysis tools, would be integrated into policies. Governments might fund infrastructure capable of real-time monitoring for swift reactions to fleeting events. Ethical considerations will also influence protocols regarding potential contact scenarios. Governments and international bodies might debate communication, non-interference, and exploration rights, establishing standards beforehand to manage expectations and responses. minimizing chaos and misinformation. These developments point toward a future where space exploration intertwines deeply with security, ethics, and diplomacy. Policies will need to be flexible, informed by ongoing discoveries and technological advances, and guided by a shared commitment to responsible exploration. As humanity ventures further into space, clear, ethical, and cooperative policies will be vital for navigating the profound questions raised by these signals. Establishing such guidelines now will ensure that exploration proceeds responsibly, safeguarding both terrestrial and extraterrestrial environments and fostering peace and understanding in humanity's cosmic endeavours. Word count, exactly 656 words. As we stand on the brink of a potential monumental discovery, ethical considerations about interacting with or revealing this mysterious object become urgent and complex. These questions challenge our assumptions about communication, responsibility, and humanity's role in the cosmos. First, what boundaries should we respect when engaging with something entirely unknown? If this object is from an extraterrestrial civilization or a natural phenomenon, do we have an obligation to reach out, or should we hold back out of caution? Human exploration history shows curiosity often trumps caution, sometimes leading to unintended consequences. Are we prepared for possible cultural, biological, or environmental impacts? How might our actions reverberate through the universe? Do we have the moral right to interfere in an environment that isn't ours? Revealing the object also carries weight. Should scientists and governments make it public immediately, or proceed cautiously, withholding information until more is understood? The impulse to share sensational news might overshadow the need for careful context. Premature disclosure could provoke panic or misunderstandings, especially among populations unprepared for such revelations. Conversely, secrecy could fuel suspicions, conspiracy theories, or weaken public trust if the phenomena threaten core beliefs or reshape understanding of life or the universe itself. Transparency responsibilities are key. If evidence suggests the object is artificial, possibly an alien probe or relay, do we have an obligation to alert the world instantly? Or should we develop a responsible, coordinated communication